Okay, so thank you for opening it up, Juan and Marco. I hope this is going to be a lot of fun. I think that some people might be yawning a little bit as I go through this, but other people may be seeing some things for the first time. So bear with me and please chime in. So if you see something, or if I say something funny, or you don't catch a command or a name of some feature, just stop me, okay? And say stuff, ask questions. So I don't want this to be just me talking for an hour about stuff you already know. Okay, so let's get going. So you want to be a developer. There's good news for you. It's quite easy. Okay, and why is that? So we use the latest development processes and open source tools that are available for projects. So we really, I think over the past 5, 6, 7 years, have sort of evolved our development process to use very standard processes. And really, I think you'll see by the end of this talk that there are a lot of safety nets in place. So it's really a playground for you to develop and work, and you can feel very free and really try some crazy things. And so I hope by the end of this that even if you're brand new, you will feel ready to hack on the code today, which is the goal. So the process usually goes something like this. We either start by forking the code, and this is what you would do if you're an external developer. You're just out in the wild. You come to the home page, you fork it, you create a copy in your own GitHub account. You can work on it that way. We also, if you're internal to the repository, we can make branches. I'll tell you all about branches in a moment, but that's your starting point. You need a copy, something to work on. After that, you're going to carry on. You're going to do your development. You're going to commit things. You're going to write code. And at some point, you might want to test that code to make sure you're not breaking what's already in the code, and maybe you want to make your own test cases so you can feel confident in your own implementation. So we can do that. At some point, we do what is called a pull request. This is basically saying, here's my contribution, so pull it into the main repository. And then at the end, we review it, it passes the test, we accept it, and you've made a contribution, right? So that's the general process. We're going to walk through this in detail. And then, yeah, it gets released. All right, so how does, where do we start? So this is probably not an unfamiliar place to most of you. This is the homepage for the GitHub repository. And by the way, you all have laptops, or many of you do. Feel free to just be on your laptop, jumping to pages, clicking buttons, and trying things, and raise your hand if it's not working. So this is our GitHub homepage. This is sort of the center of the universe for anything you want to do. And so I'll come back to this picture many times to show you where certain buttons are to click and certain actions we do based off this homepage. So this is a great place to start. And what you'll want to do to get a copy of the code is to go to the clone or download button, and it's going to tell you the address where you can do git clone in your terminal, or you can even just download a zip. I always recommend cloning a copy and having it in your terminal though, because you're going to be developing, not just using it. And I like to start with this. I'll let you read it. I like to start with this because it's absolutely true. And even I've been using Git for, I don't know how many years, and I probably know about 10 commands that I use regularly. The rest of them I Google. So here are the 10 commands you need to know. Here's the list, that list in my point of view. And I'll walk through them with you. So I'll give you their translations. So number 1, git clone, HTTPS, blah, blah, blah. That one I do have memorized. So this is getting you a fresh copy of the repository to your terminal. So this has all the information in the repo. It's important that you, so I'm not giving it a branch to start out on. I'm just saying clone the repo, which gives you access to all the Git history information, which is useful. Okay, git branch, it just lists what branches you have locally. Git checkout -b feature, awesome. We're going to talk about what feature branches are in a moment, but this is basically checking out another branch that you have there that's already on the remote repository. Git status, see what things I've changed since I last committed. Git diff, show me line by line changes of the things I've done in the last commit or before the last commit to finally commit it. git commit -am. Okay, eventually we're going to push back up to the GitHub repository. Checking out is switching local branches, git checkout develop, pull origin develop, pull from the origin develop branch, and then eventually merge it into yours. So I know that's quite quick, but how folks mostly familiar with these commands in this room? Everybody feel comfortable with git? Yeah? No? Okay.
Go through it.
Yeah, so I'm going to say a lot more, don't worry. And just ask questions and stop me if you want any more information. Okay, so I mentioned some things about branching. This is a critically important feature that we heavily take advantage of. So I would argue that this is maybe the key thing that has allowed us to scale up the development as an open source code. So very important. It's become a very popular model now for branching. And what I mean by branches is, you have a copy of the repository, but then inside of it, you can be swapping between essentially different versions that share the same development track. And so as you make commits in certain branches, eventually you can merge them or push and pull into other branches at will. And this is critical when you have a lot of people that are working in parallel on developments. So you want to have your branch where you're doing your feature development until some point it's ready to be merged into the main line, and etc. Sometimes you just want to break off branches and screw around with something and try something crazy, and you may never want to merge it back into the develop branch. But that's that's why branching is critical. Now we're using a very specific model for branching. It's very well established. I think in 2010, somebody by the name of Vincent Dreisen wrote this blog post that became really, really popular with a model for how big projects should do their branching. And now it's become known as GitFlow. There are even tools that I think automatically will set up this branching structure for you in the repository. But it works a little bit like this. So each of these swim lanes is a branch, and time goes left to right. I actually flipped this. The original picture is vertical, but I wanted it, first law of fluid mechanics, this flow is left to right, so I swapped it around. So this is time going left to right. And there are a couple things I'll start with. First, the master branch. Master branch is your stable branch, always stable. It's what you get when you say git clone and just grab the repository. You are on the master branch. And by definition, in this workflow, the master branch is always stable. This is the branch that gets released to the public. Then, one layer below that, we have the develop branch. The develop branch is where all active development happens. So this is sort of like our staging ground for going to the master branch. So as people work on the code, work on different feature branches, which I'll talk about in a second, eventually those things go into develop branch. And then at some point in time, the develop branch, we say, all right, it's time to do a release. And we start moving things up to stage for release. And then we eventually push it to master, and we have a tagged release. Okay, so that's two branches. There's master that's always stable. There's develop, where sort of all the latest and greatest things are being added. Then the magic is really when you start to break into feature branches and other sub branches where you're doing your day-to-day work. So if you wanted to develop some new feature, maybe some new fluid model, I would recommend you create a feature branch. Or in this case, I say in the slides, I call it feature awesome. You want to create your new awesome feature. So you would create a feature branch, you would start working on it, you'd make some commits, and at some point you would say, you know what, it's ready. I should put this in the develop. Yes?
Should I always branch off of develop, or should I branch off of the master?
Great question. Always branch off develop. All feature branches live down here. You should always be starting from the latest and greatest. So the develop is sort of, that's the latest development. It has all the things that are sort of cleared for release, if you want to call it that. So you should always peel off a new branch from develop as you go. Great question. Yeah, ask more, just jump in. Okay, so you're going to create your feature branch for feature awesome. You're going to go ahead and work, and at some point you say, all right, it's time to put this in develop. We'll submit that via pull request, tell you all about that also. And at that point, it's in develop, which means you're kind of done with that feature. If you wanted, you could delete that branch and it goes away. And you can trust that in the next release, when the develop branch is pushed to master, your work will be in the master, will be released. It'll be in the open source. So that's a general idea. So these swim lanes give us a lot of freedom. And this is really, as I said before I introduced it, this is critical to how we develop as a community and how we scale this out. Yeah.
So if you delete a branch, the commits that were made,
Mhm.
the logic doesn't get compressed into one commit when it goes to the develop branch?
You can do squashing. I don't know. Does anybody squash commits? I don't ever do this. You can take commits and bundle them into one and do that somehow. This is one of the things I would Google.
Are you concerned about the history of
Yeah.
how the branch was developing being lost? Right?
Yeah.
Oh, well, if you follow this process, all of those commits and their messages and code changes will go into the develop branch and then, into the develop branch and then the release.
So you
So-
don't lose anything. When you do push back to the develop branch, there's a summary, right, of what's been done.
Yeah,
Here's what the push statement.
If the concern was losing information, no. So there's another secret here is that no branch is special. They're all the same. We just have decided by convention that we're going to call one the master, we're going to call one develop, and we're going to call these other ones features and fix. But all branches are the same. And so in terms of what they hold in terms of data, there's no special branch that's master just because has some special features. They're all the same. So any information you commit to one and push into another is fully maintained. It moves around. Even you can push and pull these branches into each other back and forth, and you merge that information, it stays. Yeah.
Maybe after the presentation, you could pop up just any branch that's been merged, so you can actually see how the history is populated.
Yeah.
in the developed branches.
Yes.
So if two people make changes on the same part of the code and they try to push it up, how do you actually decide? That's something I've always struggled with.
Yeah.
Like, how do you decide which order the changes take place or resolve any?
Yeah. So Git is a lot better at this than SVN. We were just talking about this yesterday. Oh, maybe it was Tim. Maybe we were chatting about this. So Git is a lot better with conflict management. You're going to have conflicts.
Yeah.
I'll tell you right now, this is a very nice strategy, but at some point, you and another developer are going to change the same line, and it's going to throw its hands up and say, oh, I can't merge that. In general, it does very good a job at merging the majority of it automatically. So this is another reason the branching is very nice. So I'll tell you a story. We used to use SVN when we started. In SVN, people don't really use branching. I think you can do branches, but it's not really, it's not this flexible. And so what the use case, the workflow we had was all the developers in the group would just be hacking on copies, and then everybody would pour their changes into the master branch.
Yeah.
And then, immediately conflicts, or it just doesn't say anything, and the tests all break, and you're in trouble. So what's nice here is at least Git forces, because you have these separate branches, it will tell you there's a conflict right away. And then it's usually, we sort of put the onus on the developer to fix it before it gets merged into the other branch.
Okay.
So
So it is kind of a manual.
if you have a conflict, you will have to go in, locate the conflict and fix it.
Okay. Thanks.
Yeah, there's no magic way around that. You'll have to decide, because at that point, you will know, okay, I changed that line, but I should probably keep what the other person did because it's more important, or it's the right thing to do, and vice versa. So only you can make that call.
It's an incentive for doing your work in your branch quickly and
Yeah.
pushing it quickly versus
Yes, and I'll say a little more about our strategy for that. So I think over the years, we've gotten pretty good at how to manage these branches and how to make sure people deal with the pain, minimal pain. Okay. All right, before I leave this one, does this more or less make sense? So develop then eventually becomes the master that gets released. In between, we might peel off these release branches and do things like change the version number and, I don't know, update a few small things before we push it to the master. But okay, so whenever you download the code, you're on master, you can trust that it's stable. But if you're going to start doing development, move over to the develop branch and create a branch off of that, and then start hacking. Okay, so that's our workflow model.
So,
Yeah.
so suppose you have two feature branches and you want to merge them. Do you do that by merging them with develop, or do you do it by merging them first together and then merging?
You own the two feature branches yourself, or
Oh yeah, somebody else. So you have a feature branch, and I have a feature branch, and I want to merge them. Do we do that by both merging it with develop?
You can, again, there's no special branch, so you can do whatever you want.
Yeah, yeah.
If it's important to you to have them together for functionality, you should just go ahead and merge them together.
I was wondering that, are we working together? Is that what you're implying? We have two feature branches, or you're in the Netherlands, I'm in the US, and we're working on different parts of it?
It's a different model.
Well, you can merge whenever you want, and you're ready,
Yeah.
and your test
Yeah.
pass, and I can do it myself the same time.
Exactly, it's
Yeah.
completely decoupled. Unless they depend on each other in some way, then maybe you would do it ahead of time. So sometimes I'm hacking on two features, and I had an example of this lately. I was playing around with the CGNS mesh reader, and I had some problems with sorting of the elements when you read a mesh. So I put them in two different branches, but it turned out I needed to test something that required both. So you know what I did? I made a third branch, feature branch, merged those two into that, and then I hacked around on that branch. And I never push anything back to develop, because what you'll see is when we start pushing things up to develop, you're saying this is ready to go, this is finished, more or less. I want a pull request, or I want to get it into the main repo so it can be sort of solidified and stop changing. If you're still hacking on things, you might just want to merge them into each other or make a third branch. It depends what you're trying to do. You have freedom though. Do you have a particular use case? Maybe I'm missing the question.
So for instance, I want to merge with Marco's mutation stuff. So then it makes sense, for instance, to create a third branch, and we put in our stuff in there, and then.
Yeah, I would do that. So branches are cheap. Make as many branches as you want. You're not going to hurt anything. They don't have to end up anywhere. It could just be for you to prototype something. So I would say maybe make a third branch, merge them together. You probably will get some conflicts, maybe. It depends how much you've been doing. Let's see what happens, just as like a playground. And then maybe that informs some changes you need to make on your different branches, and then maybe you do merge them as one feature branch before you go up to pull request. Yeah, it's you have free, and branches are cheap, so don't be shy about making branches. You can delete them, and it's no problem. I think you'll see on the next slide we have something like 151 branches right now. So this is something we really abuse. We take advantage of this. I mean, it's a great way to do development. Yeah.
It's nice to clean up every now and then, right?
Yeah, but it's also nice not to delete things like some old features that were almost working that then you come back to maybe a year later, like the wall functions that Francisco helped finish up. So yeah. Anyway, Antonio, what's up?
In the case of merging different features,
Mhm.
if they are really updated with two different versions of the development, this can be really painful. So maybe a good practice would be to first merge the development in each feature and then merge the features together. So otherwise you will have conflicts related to the fact that your versions are really updated with a different.
So you first update it with develop,
Yeah,
and then you merge together in the third feature branch.
I think a good practice is just to merge and develop every week.
Yep.
Something like that.
I have a couple bullets about that later.
A lot of things.
We should get prices for people who merge quickly, right?
Yeah.
Well, but just pull it in from develop into your branch. You don't have to put it back into develop, but pull develop into your branch.
Yeah.
So that's one of our key strategies. I have that on later slides, so, but thanks for saying that. So you can avoid conflicts by quickly staying up to date with develop. Even if you're going to work on your feature branch for a year, 3 years, if you pull what's going on in develop into your local branch every few days, weeks, whatever, something short, it'll make it much more manageable. I mean, Edwin's been doing this for 2.5 years with high order solver, and it's been a little bit of a pain, but it's manageable. So, okay, so does this make sense?
It's a pain, but even when something changes in the developed branch that's incompatible, at least you realize it right away and not 2 months after.
Exactly.
That's critical.
So I know this looks a little confusing, and you may not be able to read that text, but branching model, you guys feel comfortable with that? Does it make sense? Yeah. We also sometimes split off fixed branches. Sometimes you'll see I'll make a branch fix _ something. I keep that convention more for like bugs. If I find a problem, something that I want to fix right away. But again, this is just all naming convention, but the philosophy is the important thing. Okay, so if you want to see all of the things going on in the code, you can come to our main page, click on branches, and you'll see something like this, which you probably can't even read. And actually the list goes through the floor, another 100 or so, right? So you're seeing a lot of feature branches. Some of these are your branches, people in the room. things like output and high order methods and error messages, down the list. So at any time we have, a lot of them are active, some are stale, they call it, so they're not being currently worked on, but they're still there. Yeah, you can go take a look at these anytime. Some of these other things we'll come to later. One thing I wanted to note is that the develop branch is protected. It's a little lock symbol here. Maybe that's not clear for you. The develop branch is special in the sense that we have put extra protections around it so that nobody can just push to the develop branch. I'll tell you what those protections are in a minute. You can see some of these are open for pull requests, which we'll talk about. You can delete them, you can throw them in the trash. But yeah, these are all just active branches, right? So you can even go take a look at the code inside of these if it's up in the public repo. That's another nice thing about being in the repo together. We can all collaborate and share these branches easily and even just go to the interface and see what's going on. Okay, how do you make branches? So you can fork the code if you want, if you're external or you just want to have a fork in your own account. I prefer to, have people get access to the repo that we're working with and just make branches right here. So what you would do is in this little pull down, you go to the develop branch and then you just type in a name, it will create a new branch. You can also do it if you have a copy of the repository in your terminal, you can just create a local branch and then you can push that local branch to the remote. I think you just add -u or something like that to push up. Yeah.
How do you get access to branching?
What do you mean? Everybody has access.
Instead of forking.
Oh, so yeah, you just have to let any of us know. We'll just give you access to the repository. Yeah, basically just need your GitHub name. We have a development team for the code. Maybe I should have said a word about that. SU2 code is an organization on GitHub. So we have multiple repositories underneath there. So if you just click on this part, you'll see, I think 5 or 6 repositories. The SU2 one obviously is the biggest one, but there's also test cases and there are a few other things there. And inside of this organization, we have developer teams. We have a development team and then I think 1 or 2 other small groups, but you want to be on the development team, which all it requires is us knowing your GitHub name and we'll add you. Then you have access directly to creating branches in here in the public repo, which I think it's a little bit easier because when it comes time to collaborate with each other, using this as the hub to push and pull feature branches to share is a little bit easier than sharing across forks. I think you have to have some special settings to share branches across forks or give people permission. It's just an extra layer of sort of complication. So, okay, so that's branching. So key message, we use branching heavily. So try it out. All right, now let's talk about development. So now you've got the code, you know enough about GitHub to be dangerous, Git commands to be dangerous, and you're ready to start working on the software. So if you pull up your directory, here's what you're going to see inside of the SU2 folder. The first thing is a handful of folders that contain the C++ code, and these are in folders that are named that match the name of the executable. So SU2_CFD, DEF, DOT, Geo, Sol. These are where the majority of the lines are code lines, and in particular, the most are in the CFD solver. I would say like 90% of the C++, 80, 90, and the common folder. So this is where you want to look if you're trying to get into the C++. In SU2 IDE, we keep a couple of project files for IDEs, for integrated development environments. In particular, Xcode is there. So if you use Mac, I use this all the time. We have an Xcode project already available. So you can just open that up and it's already set up to compile and run for you if you put a test case in there. So it's nice for debugging. It's nice for in the IDE to be able to jump around. Everybody probably has their own favorite tool. With a big C++ project like this, it's very nice at the start. I know it can be overwhelming if you can do jump to definition and learn the classes that way by bouncing around the files. It'll just save you a lot of trouble while you're getting going. Okay, so IDE files, the Python scripts. So
you've done their files for other IDEs as well.
Yeah, I think we have Visual Studio, Wing, and Eclipse. The other ones I can't say much about. Has anybody used the one of the IDEs other than Xcode that we ship with the project. Anyway, we can give it a try later.
Yeah, Code Light. Yeah, so we actually set it ourselves, but it's.
Is this the Microsoft one?
No,
Code?
No, it's a lightweight.
Okay, I don't know this one. Maybe we can take a look.
I've also used Eclipse, but I wasn't actually aware of the. I'm not sure if you actually have a project file there, but I actually set it up.
We used to. It could be that it's out of date. Maybe we could take a look. Another one I found recently. You guys probably know Microsoft's making a big push now toward open source and whatnot. They've made a lighter weight version of Visual Studio called Visual Studio Code. If you guys tried it, it's actually quite good. It's kind of like Xcode in a lot of ways. I was using that on a workstation. I think we toyed around a little bit with that at Bosch. It's not bad.
And it works well with Python.
Sorry?
And it works well with Python.
Have you been using it to?
We are using Qt, but this Visual Studio Code is recommendable in the sense that if you're developing the Python scripts.
Yeah.
And all this.
Yeah, it's able to.
Go to
It's able to understand C++, Python. You can download packages and customize it. It's pretty good. You might get it.
What is it called? Visual Studio?
Visual Studio Code. Yeah, free, open. It's actually, I was pleasantly surprised. I was like, oh, okay, I'm going to download a Visual Studio.
Obviously runs on Windows, so
I don't know if it's open source, but it is free. I know it's customizable, but yeah, it works on all platforms.
I thought it was just.
No, it's, I never thought I would stand up here and say something like this, but try that Microsoft product. That's quite good. Maybe I shouldn't be advertising. Anyway, okay, so I'm starting with code pieces. So we have the C++, and then maybe I jumped before actually saying the Python part. C++ is probably 2/3 of the lines of code we have, but then the last third or so is Python. So we have quite a few Python scripts and a whole sort of class, structure that lets us do things quickly, like manipulate config files, move files around, orchestrate all the calls of the C++ executables, and even a full wrapper now. We have the entire C++ part wrapped up in Python. So there's a lot of Python in there. You can find that all in SU2 Py. So if you go in there, you'll see some folders, and that's where you want to look if you're wanting to develop the Python parts. Externals, this contains source from other projects that we ship. The intent is not that we should really be changing that much. We typically don't change the code we put in there. It's mostly just for a convenience for people downstream. When they get our repository and they build it, we want to have a few components in there that will automatically get built and linked, so they don't have to go get them. So it just makes it easier for portability, usability, just making life easier on the user. And then we have a couple test cases that are always there. So the quick start always has the config in the mesh. So the NACA 0012, the classic Mach 0.8, 1.25 angle of attack problem. So often if I'm building on a new system, I'll just hop in, download the repository, build things up, and then jump into the NACA 0012 and just test that everything built okay, run it, run the flow, run the adjoint, try the Python scripts, just see that everything's okay. So we ship that for that reason. And then test cases. We'll talk a bit about that later, but there is a folder here, test cases, and in the code repository, you're only going to see the config files. You're not going to see the meshes, and I'll explain why in a little bit.
Same directory structure.
Same directory structure. Lastly, we try to keep a up-to-date config template file for you. So as an open source code, this is one of our sore spots, is managing all of our config options, and we have no GUI, so we're always working on this, looking for good ways to improve it. But if you're ever unsure, you can hop into that file and check out all the options that are there. So you can use it to start a new case. I actually recommend you find a test case that is closer to your problem and use that as a template rather than starting from the config template. But I often go back in there and copy options I don't have and add them to my files. Lastly, if you're ever messing around with files and you move things or you add files and you want to mess around with the make system, this can get a little complicated, but the first thing you should try is to run the bootstrap script we have in there. So if you're getting weird compile errors, it can't find files, auto tools is just breaking on you when you try to configure make install, try to run the bootstrap that's there. So this will reset all the make files. It will actually build and install an old version of auto tools for you and try to reconfigure and give you a working set of make files. That's the goal anyway. Okay, so those executables I talked about, I'll just flash them up on the screen. The primary one, if you're doing anything related to PDEs on meshes, you're probably going to be working in SU2 CFD. There are some other important ones though. So SU2 Sol for solution export. So if you run the CFD solver, maybe in parallel, it will write restart files in parallel, but you might want to generate multiple different types of output files. So you would run this executable with your restart and generate your visualization files, for instance. Deformation, so we use that for multiple things. As a standalone executable, it's typically used for shape optimization. So in between your flow, adjoint, deforming your mesh to get to the next design step, that's typically where it's used. But the same classes are used inside of CFD to do things like unsteady flows with dynamic meshes. So we share a lot of classes. So even though things show up here, a lot of the same code is in these executables. Projecting gradients for shape design, geometric analysis of, say, cutting wings and getting volumes and thicknesses and things like that. So we have a tool for that, Geo. And MSH, which hasn't been used too much in the past years. We keep it, but it's mostly legacy at this point. And then a few Python scripts that you'll probably use most often. Parallel computation will essentially just automate running of SU2 CFD and calling SU2 Sol for you. A few others, the critical ones are probably shape optimization, the different adjoint scripts, and finite differences, direct differentiation. Those let you compute a flow, an adjoint, and a gradient, or just in the direct cases, flow problems that lets you compute a gradient for shape design. But okay, I don't want to go into too much detail there. We'll let you guys explore that. Okay, so just a word about philosophy, because I'm going to go into some of the C++ classes. So before we do that, what we try to do is set up the classes so that we can have as much code reuse and have good data encapsulation. And the idea is, of course, code reuse is nice because we minimize things. We're not copy pasting the same function over and over again. So we try to reuse classes in as many places as possible. And then the other idea here is by making sure that they are modularized to some extent, you can basically focus on one piece of the code. If you want to start developing, you do not need to learn all 250,000 lines of SU2. You can jump straight to the thing you want to do, work on that, and you can trust that in most cases, you're not going to hurt anything else. So for instance, if you want to work on linear solvers, you could basically go to the linear solvers file, and there are a few well-defined matrix and vector classes, and you work there. You don't really need to know anything about PDE solvers. You can avoid all the other classes. In theory, this works. This is true most of the time. There are always, of course, exceptions, but in general, that's the way we try to architect it. Another example, if you don't want to worry about MPI, in particular, yeah, I mean, you probably can get away without doing that. If you just want to focus on, say, how do you compute a convective flux, you can go straight to working on the numerics level and just worry about how I compute a flux at an edge and just forget all about the mesh and the MPI communications and all that stuff. So that's the idea. So that if you want to just work on one thing, work on your area of expertise, you can do it. That's important. And I already said this a little bit, but we do have these common classes. So things like grids, linear solvers, output. If you don't want to deal with how to write a pair view output file, you don't have to. That's in another place. That's done for you. And we reuse it across many PDE solvers. So things are well separated. Although we're always working on improving input output a little bit. And I'm looking in the back of the room because I know guys are hacking on this today, right? So, but this is the goal. This is the philosophy that we're trying to get to. So we reuse those base classes wherever we can. And in particular, those are the ones that are in common. So in common source, those are the ones that get used most heavily across multiple solvers. Then once you decide you're solving a particular PDE, this is where we start to get more specific. So a lot of the stuff above that is reused everywhere, but then you decide you want to run a flow problem. So now we need to get more specific. And in that case, we create iteration, numerics, solver, and variable classes, and those are customized to the particular thing we're solving, the particular governing equations we have. Any files that end in an underscore structure, those hold base classes for what comes beneath, the specialized ones. So if you see underscore structure in the folder, that is going to have your base classes. You can go there to get a feel for what, all the sub solvers and numerics classes have inherited from up above. And then if you want to see specific implementations for PDEs, you'll look for solver underscore wildcard for, say, direct mean. So if you want to see what we're doing for the mean flow, you would look for solver direct mean, numerics direct mean, and variable direct mean. I'll tell you what those are in a second. But this is the naming convention we try to use. And I think for the most part, this is, it's across the code. You can see this. If you look in the SU2 CFD files, this will become very clear. Okay, this is probably going to be hard to see in the back, but I want to at least walk through one instance, if you're, say, going to run a RANS case, what the key classes are, starting from the top down. So if you were to take our Doxygen information and just generate the graphs for all the classes that are called by SU2 CFD, this is what it looks like. I know it's quite messy, but I'm just going to focus on a few. And so in this case, we're breaking the first law. It's going right to left. But yeah, I think so. Yeah, I like to walk. I like to walk and point. Don't like to stand it. Okay, so let's start with the driver. So this is where it all begins. Driver is, if you look in the main file of SU2 CFD, CPP, it really doesn't do much. It's a main call. It gets a few pieces of data, sets up the config, I think, or at least the first version. And then it essentially sets up one big class that starts your multi-physics problem. That's the driver. The idea is that then folks can write child classes of C driver that are specific to multi-physics problems. In this case, I'm doing a RANS flow problem, so it's just a single zone, single physics kind of problem. But you could do other things like FSI. We have more now. This is a little out of date, and I think some of the names have changed. But you get the idea. If you want to create some new problem that needs multiple physics, you would start here. Today, okay, we'll just say we're going to instantiate a C fluid driver. Config class. This is what you would guess. This is just a class that holds all of the config file options for you in a map, and then getter and setter methods to get those options. So, nothing special there. Iteration. This is the first level where we start to get specific to a physics, more or less. The idea with the C iteration class is this is what you would write to perform one iteration of a particular flow or heat or structural problem. So if you imagine you have boxes for flow and structure and heat conduction, this is what you would write that describes an iteration of one of those, which are then going to get coupled together somehow in the driver. So this is where we start to get specific. So in this case, we have a flow problem. We're just going to instantiate a C fluid iteration, which tells you, this drives the loop to how I actually compute and update a step of the fluid solver at a high level. This is all very high level right now. Next is the solver. So the solver class is where we finally describe what the terms in the PDE, what they look like, how you actually solve them. So in the solver class, you would do things like compute the loop that computes the convective flux, and you'd have the loop that computes a viscous flux for a flow problem, boundary conditions, pre-processing, post-processing, all the things you need to compute the spatial terms in the PDE, at least the loops that drive those terms. That's in the solver. In this case, it's a RANS problem, so I need a Navier-Stokes solver, which inherits from C Euler, because they're so similar, and I need a turbulent solver. In this case, I am using SST, and inherits from C turb solver. So those, again, describe what I actually need to do to compute those terms, and source terms, I didn't say that. Those would be in there. Variable class. The variable class, think of it this way. At each node in your grid, at each degree of freedom, you have some set of variables for your PDE you care about that you want to store. And so at every grid node in the mesh, you have a C variable object. And in that C variable object, you put your important data. maybe pressure, Mach number, primitive variables, etc. for a flow problem. They live in the variable class. And then there are getter and setter methods to get things out, in and out. So that also mirrors the solver and the numerics in that we have essentially the same classes, the same naming roughly for a variable now. So we need a CNS variable, inherits from Euler, and a turbulence variable for SST, inherits from the base class. Numerics, we're finally getting down into sort of the kernels where we compute actual fluxes and do the heavy lifting. So in numerics, that's when you're getting down to the flux level. So in numerics, you essentially just imagine you have data at points I and j, and you want to compute a flux at the interface between I and j. You're down to that level. So very much a kernel. And so you'll see stuff like the row flux method. I just pulled that snippet out. So this is where you'll actually start to find calculation of true flux schemes and source terms and things like that. And that structure is the same. So you'll find numerics underscore direct mean, et cetera, et cetera. Okay, so far all I've said is stuff about spatial integration, but there are common classes for any PDE that will take care of your time integration also, or relaxation if you have a steady problem. And we have classes like multi-grid integration or single grid integration, pretty self-explanatory, but you can also add new ones. Let's say you have a slightly different scheme, like you have the DG high order solver. You might need to write a different time integration loop that doesn't take advantage of sort of a classic multi-grid or single grid integration for a finite volume method. So this is your chance to implement some kind of new time integration schemes. You can do that here. Lastly, output. So this is something that's shared from everybody. All the solvers can call more or less the same routines there. We need to break it up a little bit to make it slightly more user-friendly, but the idea is that all the solvers can call the same routines to merge the data for you in parallel and write pair view files or tech-plot files. And you shouldn't, as the writer of a specific physics solver, have to worry about how do you write a pair view file. This is going to be taken care of for you. So as long as you put the data in the right place, everything's going to be merged even in parallel, and it'll write files for you. So that's where we're going. Okay, how are we doing? We should speed up a little bit.
Tom, can I ask a quick question?
Sure.
It's not specifically related to this topic, but let's say that I would like to, the SU2 solution file has certain fields.
Mm-hmm.
Okay, so you have coordinates and then you have conserved variables and so on. So what is the general, let's say, approach that we should consider if we want to add more variables? Just make a quick example, very practical one. With Gaetano, we are thinking about adding, for example, all criteria to identify vortices, Q criterion, blah, 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 and so on. So what should we do? Should we leave it on a Python and do something outside, add it there? Because it can be very...
So there's a short answer and a long answer. I'll give you the short answer. Some guys in the back can maybe give a longer answer, but we've had this problem for years. What's been happening over the last year or two is we've been moving, this is an example of how we change the abstractions. So we've been moving where the data, let's say, interfaces. So what we've done is we've broken off little routines that in the end, we intend for them to go into the solvers. And in those routines, you specify on a per node basis which variables you want, and you register them. You give them a tag, and they will, you set them to a particular array. And without you doing anything downstream or even looking at output, it will be taken care of for you. So you will be able to customize that very easily. And actually, it's already there if you want to do it right now. You'll see a load local data underscore flow. If you go in there, there's step-by-step instructions just how you can add more tags and more data, and it'll happen. Now, the bigger question, which is why I said the guys in the back might want to say something, because I think they're going to hack on things related to this today. So you'll hear all about it, I think. Yeah, we know this is an issue. We have already, we've been working on it slowly for a year or two. And I think some of the complicated parts with parallel IO are done now. That's been improved over the past couple of years. But the class structure needs to keep moving. So yeah, smarter guys than me will tell you how it's going to happen. Okay. So I think actually we're through the thicker part. So I know the bar is only up to through development, but we're actually
No rush, no.
cruising. Okay, we're doing okay? You guys are awake? Need more coffee? Yeah. Okay. So now you know the basics. You're ready to start your branch. Feature awesome. You're ready to start hacking. But you might say, wait a second, how do I coordinate what I'm doing with other people in the repository? So if I'm just going to start hacking, I want to make sure that what's going on, I'm not duplicating work, etc. So the issues in GitHub are a great way to start. If you just say, I'm hacking on this thing, but I don't know, is anybody working on this? Or I have a proposal, you can leave a note right there. Or contact the developers around here, just shoot an email, let us know what's up. Over the years, this has been pretty easy. As we keep gaining developers, we're gonna work on how we organize this a little bit better. But for now, just start with writing an issue on GitHub, and the community's there to help you. But then you'll ask, how can I make sure I don't break what's in the repository? So this is the first concern I always hear when I'm helping, say, a new student get started. They're a little concerned about making changes because they'll think, it's gonna break everything. I'm a little timid. I don't wanna, and we have a great answer for that. So continuous integration is what's gonna save you. So this is something that's integrated directly with the repository. You don't need to worry about it. I'm going to show you how it works, and you can rely on this so that you don't have to worry about breaking what's in the repository. Okay, so how does that work? If you go to our main page and you scroll down a little bit, the main software page, you'll see the README. And in the README, I'm not sure if you ever noticed this little button here, but if you click on it, you probably thought, what's passing? What does that mean? If you click on it, you're going to go to our Travis CI page. And Travis CI is for continuous integration, is a free service. So it's a standalone service. They have a commercial version too, but it's a service that will go ahead and in the cloud, basically boot up some workstations for you and run your continuous integration tests for you. Since we're open source, they do this for free, and it's fully integrated with the repository. So at any time, while you're sleeping, probably right now, I bet if you went to the web page and clicked on that button, you would see something running. So our develop branch is being tested very, very regularly, and all sorts of other branches, which I'll say more about. But this is happening, in the background all the time. And what is it doing? So it is taking a comprehensive set of about 200 test cases. I think I need to recount, but it's about 200 test cases that the developers have put together that test correctness for a wide range of problems. So config files and meshes go in here, and it runs a whole suite of cases. And if any of the residuals change over a certain tolerance, we get an email if it's broken. So if you look over here, it tells you a lot of info, but basically this is, I just grabbed a snapshot of one of the latest tests. So this is, I think Edwin had pulled in one of the pull requests. He had pulled in the code. So that kicks off the regressions on the develop branch, because the develop branches are sort of key branches that holds all the development. And you'll see it's running a suite. This is a matrix of, whatever we have here, I guess eight different sets of tests. Inside of each of these, it's doing it in serial, it's doing in parallel, it's running with automatic differentiation, it's running the Python scripts, it's testing a ton of things. So inside of each of these, you get a printout of all the tests that passed or failed. And in this case, they all passed, so it just gives us a check mark. No emails. But we rely very heavily on this. This is sort of a backbone for how we keep expanding the code, because we can feel confident that as we develop things, we know it's, we're maintaining, we're not hurting any previous capability, everything is fine. So what can you do? Well, it turns out you can also activate this for your own feature branches. So I highly recommend you do this as you are developing. So if you click on branches at the top in that interface, you'll see a whole bunch of branches that have turned this on inside of their own development branch. And myself, I'm not having much luck. I've been working on this one for a while. I got a bunch of X's. Okay, but that's all right. The idea is that in your own branch, as you were developing, you turn this on, you set your email address and your branch name here in this file called .travis.yaml. And when you do that, and then you start to push your changes up to the GitHub remote, it will automatically kick off the regression tests on your changes, on your copy with the feature changes you've made. And then you will get an email if it breaks. This is really important. Make sure you change this, because otherwise it'll email the whole developers list about your branch's problems, which it's okay, but you probably just want to email yourself. But this is very, very helpful. So as you're developing, I mean, with each commit and push up to the remote, you can know that you're not breaking any other tests, that you can feel confident that you're doing the right thing, everything's working. And if it does break, it gives you very valuable information. It shows you which test has broken. It gives you the whole printout of the console. Did the residuals change for this one case? Okay, then you can go investigate. You know exactly where sort of to look for problems. So yeah, I highly recommend that as you make feature branches, you activate this for your own work. It'll save you a lot of trouble.
This is also a precursor step to try to merge anything back.
Yep, coming there. Yeah, it'll save you the time.
Does that mean that you have to make sure that locally that works first, then you commit it? Or
no?
Is it checking the other parts of the code that you're not breaking them while?
So you don't even have to do it locally. If you just make these two changes, these are inside of the main repository. If you make those two changes and you commit on this branch, so remember the branch is just your own little development line. It's sort of a standalone thing. You can push that branch up to the GitHub remote. And once that happens, it's going to take your branch, which has everything. If you've started off of the develop branch, wherever the develop branch was when you started, it will run the tests on that. And develop is always stable, by the way, for the tests. You'll see, because we don't merge anything into develop that isn't stable. So you're going to start from a stable version. You're going to create a feature branch. You're going to make your changes. You'll add these two things, push it to the remote, and then Travis will go ahead and in the cloud grab that version and run everything for you, all the tests that are running on the develop locally, and let you know.
It is an amazing capability, and it's amazing that it comes free, right?
Yeah, yeah. This was a game changer, I think, when we started using it, because we used to have, along with SVN, you remember we used to have a little workstation in the back room of your lab that was on its last legs and I thought was going to die any day, with a handful of regression tests that had to be manually checked, and we had to, like, I don't know, pull a copy from SVN over on that machine every time we commit. That was a nightmare. So this is amazing. So not only that, but you should also add your own test cases. So this is where it really gets interesting. So you're doing your development, you're not breaking any of the old test cases, but you have a nice new feature. And if your intent is to put it into the develop branch, you probably want to protect your feature. So I recommend that you also add 1 or 2 test cases for your own problem. They should be small, lightweight. Again, the idea here is just correctness. You're not worried about running a big validation or verification or validation case. This is just run a small case, small mesh, something that tests the particular feature you put in for correctness. Something you feel confident that if the residuals change, or maybe you can do a file diff, if a file diff changes, you know it's broken. So this is the idea. So to do that, you'll find there are a couple scripts inside of that SU2, inside of the test cases folder. Serial regression.py, parallel regression.py, and a couple others. Most of the infrastructure is already there for you. All you need to do is take, let's say this example, like the NACA 0012, is take one of these and copy it and change it for yourself. You can use this as a template. So to create a new test, basically you need to give it a name. You need to tell it where the config file is located. You need to tell it what the config file's name is, how many iterations. This is the key one, the test values. So it's going to compare, in this case, the last 4 columns of the console output. So basically the residuals at iteration 20. That's what it's doing. So when it runs the calculation, it's going to run all these tests. It's going to pull the lines. It's going to do a check on the values there. If they're different within this tolerance or by more than that tolerance, it fails. And that's when it emails you. And then there's also a timeout, so it doesn't run forever, something like that. But that's it. If you copy this, paste it, change the names, put in your own case. I'll tell you where to put the configs in a second. Set the residuals. and push it up, you have a new test case. Everything else is taken care of for you by Travis. Don't need to do anything else. Yeah, I already said that. So if it fails, you're going to get this email. You'll be able to click on it, go in and look at the whole console output, see the case that failed, and investigate it. Okay, I think Juan already brought, oh yeah, question.
So the test case only tests for like residuals and all that. It doesn't test for any value like.
So it will be whatever the last 4 columns are. So in this case, it's an implicit problem. So this is residual, lift, and drag. So in that case, it is testing forces.
But you could.
We can do whatever we want. There are other cases. I'm just giving this example, but we have things that will diff files for you. So sometimes you have a whole file that comes out with, say, gradients from a finite difference calculation, and you just want to check that they're identical. The whole file is identical. So we have the ability to diff. The nice thing is, I'm not giving too much detail, but Travis is really just a nice cloud service that will pull in whatever you give it, run it, and report back. We have the classes that actually call these scripts. We had written them before we started using Travis. We already had the capability, and you can do this now. Go to the test cases folder and just run serial regression, and it'll run locally. So we already had this structure, and we can change it however we please. Travis just needs to know the key thing to tell you whether it passed or failed, and we just happen to give it a Python script that uses this. But we could do whatever. So Travis is just the platform. We can customize that.
Philosophically, there's this issue of coverage in a suite of regression test cases. So it is important to make sure that when this suite runs, you're testing the capability of the majority, if not all of the solver or all of the code in some senses. But it's more than that. It's also protection for you in the future. Right?
Mm-hmm.
This is critical. If you know that there are certain values that must be met when you run 5 iterations of the solver in whatever feature you had, the responsibility is for you to create a test case or a regression case that ensures that that is always held. So when I change the code and your output changes, you know that something's broken, and I won't merge those changes until we talk or we fix it or something like that. So as the cases go along, we start trying to cover the entire code.
Yeah. It's as much about saving you headaches later as having the tests for. Yeah, it's important.
In fact, in some senses, when the entire suite runs, it would be nice if every single executable line in the code was exercised. That would be 100% coverage.
Ideal. Well, yeah, we have certain practical limitations like Travis times to run and blah, blah, blah. But yeah, critically important. I would say this and branching are the 2 things that let us scale out and actually develop decentralized and in parallel. I mean, I think without this, it wouldn't be happening. Okay, so Juan already brought this up earlier, but we have a very particular way to store those files, and I like to think it's pretty logical. Yeah.
So from the regression, there was some like
Yeah. So we can diff files. So, and if you have some new use case that you need for your new feature, just let us know. We can. There's another class underlying this in Python, testcase.py, where we can write a custom test. So here, it's just saying, test list here is it gets called a special function below that, but we can customize that function to tell it what to actually do with these numbers. So yeah, if you need some new way of checking correctness, just let us know. That's a good point. It can be any output you have. Okay, so in keeping with this comment that we have some practical restrictions on sizes and time to solution and whatever for the regressions, we separate out the data, the static parts, from the config files, the things that sort of quickly change. And so when you create a new test, the second step is to put the config files and the meshes in the right place. And those are in 2 different repositories. So as I said before, we have this organization with the SU2 repository. We also have in that same organization a test cases repository. So the philosophy here is put the lighter weight, more frequently updated files in the code repo. So as you're hacking, you're more often writing code and you need to change the config file to get the test to work in the code repo. For stuff like a mesh, that's not going to change, or maybe like a restart file or something that doesn't really change and it is larger, we want to put it here. Now, the important thing to note is they have the exact same directory structure. So when it comes time, Travis pulls both these repositories and just does a CP -R and merges them together in one line. So then these meshes end up in the same folder as that. Everything gets called for you correctly. But the idea here is just to separate out the large files, because when we were first doing regressions with the old system, we just threw everything into one repository, and then it would take an hour to download a gig of stuff that's in the SU2 repo. So we don't want that. We want the code repo to be a little bit smaller, faster to download, and then this has all the big files. So we separated that. But again, key thing is that the folder structure is the same. So you look for the same location just in those two places. Okay, so now you know all about regressions. And let's say you finished your awesome feature, you checked everything's okay, you added tests, and by the way, you made sure there are no new compiler warnings and the style conforms to the standard. You can just mimic what's there. There is also a style guide on our GitHub page. Check it out. But you're ready, you've got it done. So now you say, all right, I would like to contribute my feature. So what do I do? Because right now, it's just in a feature branch. So if somebody downloads the code, I mean, they could switch onto your branch and play with it, but it's not in a release, let's say. So how do you contribute? So the first thing you have to do is get it into the develop branch, stage it in the develop branch, because again, remember that gets pushed to the master and becomes a release. So to do that, we use the standard pull request approach. So well established, we're gonna use pull request for this, and I'll tell you all about it. So once you're ready to contribute, it's time to do a pull request. And if you come back to our main page and you hit the pull request button up top, you'll see all of the active ones that are open right now. And in that list, you'll see who opened it up. You'll see a few things about progress and whether it's been reviewed and the status. In this case, let's just say we want to create a new pull request, so we click that button up there. And again, the idea is that pull request means we're requesting to the project to pull in our work. So this can also be from an external fork. It doesn't have to be only an internal branch, but this is really your call to the project to say, hey, I've written some stuff that I want you to pull into the main line, so consider it and pull it in. So here we go. What does it look like? So if you click new pull request, there are a few things that are going to happen. First, you want to make sure that you're submitting your work to the develop branch. So at the top, open pull request, you'll see these two pull downs. You'll want to make sure you're trying to contribute it to the develop branch, again, because that's the branch we've designated for this type of work. That's where we stage everything. And here you're going to see your branch. So the other night I made a branch called Feature Awesome, and I fixed a typo. Okay, so I say, this is an awesome typo fix. Guys, you guys really need to pull this in. This is my pull request. So you'll have a chance to fill out the subject. We also have a template for you, so you don't even have to think about what to put. You just come in here and it says, give a brief overview in a few sentences. I'm fixing an important typo. Here, you can list any related work. So you can reference other issues by putting hashtag and the number in your pull request. So you can say, this fixes issue number, blah, blah, blah. And then there's also a checklist, which are just a few things that we want everybody to do before they, while they're working on the pull request or before they put in the pull request. And I've already mentioned it. Things like warnings, making sure there are no compiler warnings, making sure you're submitting to develop, making sure it has the right style, and if you have them, making sure you add a test case. So this is where we are trying to remind you guys, put in a test case for your pull request if you need it. And yeah, fill out the PR template that tells you what to do along your way. Makes it easy. Then you say create. So there are a few reasons why the pull request method, I think, is really, really important for how we do the contributions. One, it keeps everybody informed. So the moment you click create pull request, everybody that's watching the repository gets an email. And they say, Juan is trying to push in his new feature that fixes the parallelization. And he's listed out all the things he's done. It even collects all the commits he's made. You can click on it, you can go through the work, you can see what's happening. So even if nothing else happened, all the developers now know that he's got a new thing he's working on, he's committed it to the branch, and it's there. or well, it's there to look at. It's just as a pull request. Nothing's happened yet, by the way. This is just a announcement to the group.
I think that's clear because people are normally afraid. Initiating the pull request, just initiate things. It's not going to break anything. It's not going to do anything. Right?
This is just an announcement shot to everybody. Hey, I've got this thing. Think about it. Because the next thing that happens is the community starts to discuss it. So this offers an opportunity to discuss and review code, which is critical. So we all work in a big community. We all have experience with different pieces of the code and have expertise in certain areas. And some of us wrote certain parts of the code. So we are the best ones to help somebody make changes or check the quality is okay. And so that's what's happening here. So if you look up above, this is my pull request from the other day. And I sort of hurried and got it in, and basically Edwin perks up and reviews my work and says, oh, this looks all fine, except the white space is all messed up. So you have to fix the white space before we merge it. But that's perfect. This is great. So I like that. He requested changes, right? So code review by fellow developers checks for content and style, and also just organization, improvements, what can you do better? I mean, this is super helpful. So this is our chance to really work together and improve things. So that's step 2, code reviews. Not only that, but it is required. So you cannot contribute anything until at least one person has approved your work. One other developer has clicked approve. And so this is not getting merged because Edwin has requested changes, meaning it's blocked. It is blocked until I fix my white space problems, which white space problems are a lot of fun. We've had a lot of those. So that's one. It's an opportunity, and it also is a protection. Number 2, regression tests. So not only were you running it on your own branch and you feel confident that everything's working okay, but the moment you open the pull request, it fires off the regression tests on your branch, well, merge with develop, and double checks that everything's working. And that is also a precondition for merging. It will have a big X there if the tests break, and you actually can't merge it, it's blocked. So there's no way you can merge in something that breaks the tests. So that's the second level of protection. So you can see, we have a very controlled gate for how we let things into the repository. This is not the Wild West. This is very standard open source procedure. This is what all big projects do, more or less. So we have those 2 things. But see it as an opportunity to get your code reviewed, to work together, to look through. I mean, you can click on every one of these commits and see. And GitHub has a nice interface now for actually giving reviews. So you'll go in and say, I'm ready to review. You just look at it, and you can leave comments on the specific lines, and it'll track it for you, and you can submit your review. They just put this out within the past year, I think, the formal code review interface. It's relatively new, but it's really nice. So once those things happen, then finally you can have things merged. But
could I make a comment
please.
and ask for your input on this? One thing that's always worried me about SU2 from the beginning is the idea that if you have 200 branches and everything gets contributed, the eventual master branch is going to keep growing and growing and growing, perhaps like OpenFOAM did, right? So, and get out of control. So for me, this also provides an opportunity to say, well, that's a great contribution, ISO, for example, but maybe this needs to be an external script outside of SU2 that post-processes a data file. It doesn't need to be into the code, or you know what I'm trying to say. It's going to be affecting future development of the code and make certain things impossible. So there is a possibility that if all the checks pass and it's a beautiful contribution, you know, that contribution may not make it to the master branch as part of the code, but maybe as part of an associated file or something else, right? So,
this is why the code reviews are critical. I mean, I agree. It's.
But it's disappointing for NISO to work for 3 years and then come and merge things. So I do encourage people also to talk to people about what you are developing and intending to merge a year, 2 years, or 3 years later, so you don't have that disappointment.
Exactly.
Right?
Exactly.
It could have benefited from some input from the community early on to decide more or less how that should be integrated with the code.
Yep.
Just one comment on that. I mean, you don't have to wait until your feature is finished to open the pull request.
Yeah.
So you can also open it when it's not finished and not working.
Exactly.
Because you can just add commits after that, and the pull request will be updated with the so just
and
open it even before, no problem.
Perfect. And add just start an issue. Say, I'm new to the project. I want to hack on I don't know, this new solver for something. What's going on in the repo? Is anybody working on this? Or how can I improve what's there? Perfect.
In the end, who will decide this? So will this be, so suppose I want to have a look at something extremely specific, only interesting for me. Who will say, but that's not really something to put in the main branch?
I'm depending on the community to come together and discuss that. And we have a lot of good discussions like this on the boards. I don't know if you go through and look through, we have some really nice discussion around pull requests on improving things, changing things, taking this out, adding that. I trust that the community can take care of that.
It is a community decision at the end. But, I mean, I'll give you an example. One of our former students, who nobody in the room knows, developed this great capability to do gust responses inside of SU2. Right? Of course, he was very excited about putting it back into SU2, but I think at some point we decided, you know, having all that extra code for a specific thing, which is a gust response for a specific airfoil, it's probably not the right thing to do. Maybe you can take some time accurate boundary conditions and something else, or maybe just have it in your own branch, and some of those things never get merged. And
there is a
we have to be
fine,
mindful, right,
yeah,
of this balance of more capability and just making the code just unmanageable for new people to come in and contribute.
Yeah,
I worry about that all the time.
Yeah.
So do you also see development where it will be very easy for users that have very specific problems to keep these pieces of code for themselves and code it easily as a external library to do? Or something?
Well, I mean, we write a lot of interfaces for different things. I mean, as you know, I think we're always working on where the class abstractions are so that we can plug in different things. I mean, modular is always the way to go. So I think that's what you're asking.
In
But-
some sense, something that gets contributed to the code needs to be leveraged by others, right? So if it's a very esoteric, very specific thing that you're doing just in your lab, maybe it never gets merged back into SU2, but then you have to, if you're going to use it forever, then you have to continue to make sure that you're synced with development with the master branch. So I don't know what the real answer to that is. You probably prefer to have it up there in the master branch, right? I don't know what the community would say. Maybe others can speak.
Yeah, there's always been a fine line between encouraging people to contribute and managing and trimming. So I mean, over the years, you don't see it much, but we trim a lot of stuff out of the code over the years. So some of the examples that Juan's giving, things we put in the code very early on, we've deleted a lot of things, unfortunately. But this is the thing: if you can't maintain it, there's nobody working on it. This is the sad fact of life. It's better to trim the code down and have it be a little more manageable, robust, than to just keep growing. So this is always active. There's always push and pull. I mean, we try to encourage as many people as possible to get involved in this process, because I really believe the more people we have in the community, the better the quality of everything. I really think this can scale that way. But we have to be thinking about the other side and controlled. So this is critical. Having people that know the code review things and say, you know what, this isn't quite right, or you need to clean up this, or maybe this doesn't belong at all. Sometimes, yeah, there'll be sort of tough discussions, but
It's rare.
I think it's pretty rare. So far, me personally, I'm not as concerned about that yet. I think we have a lot of room to grow for now, and things are architected nicely such that we can sort of grow, the classes out. I'm a little more optimistic, but we have to keep our eye on it. I mean, that's going to be the story of the next however many years of the project. So. Okay, good question. All right, and if I got lucky and they passed, so coming back to this pull request concept, in my case they passed, but if it failed and you got a big X here, you can click on details and it'll take you to the page where all the pull requests are running. It'll show you yours specifically, but I put up the page here for all pull requests just so you can see. So all the pull requests are, they're actively being run in the background by Travis. Okay, so once that gets merged and accepted, you're done. It's in the develop branch. So then later when we decide to pull off a release, your work is out in the wild. It's out in the open source. Your feature is released. So at some point, I didn't belabor this point, but eventually we take that develop branch, we push it to master, we tag it, we create binaries, we can script a lot of this. Although there is still some overhead. We advertise it, and the feature is released. And so on the GitHub page, you can just click on releases. I don't think I have the button, but there's a releases button at the top. You click on that, you'll see the latest release. We always put a little description based on some of the commits. You have the source code, etc. You can download binaries for a few machines off of that page. So it's out there, it's released. Okay, but the story's not over. Actually, your work isn't done. So documentation and tutorials are critical. So if you really want your work to get noticed, it's one thing to put it in the open source, and that's fine. But it's possible that nobody's going to see it or know how to use it. So test cases, adding test cases, critical. Documenting and adding tutorials is the next step. So if you want to get some visibility, put it in there, amplify your impact. I highly recommend this. I mean, documentation, nobody likes documentation, but we all know it's critical, okay? So, and the way we can do this, lucky us, it's basically the same process. So over the last year, we have moved all of our documentation out of old, horrible ways of managing it and put it into GitHub. Our main page is in GitHub Pages. It's a repository like any other. Our tutorials, our documentation is all there. So if you come to the main page and you click on Docs or Tutorials, you'll see all of it here. You'll also notice there's a button that says Improve this page. If you click on that, it's going to take you straight to the repository where this lives. You can directly modify the text right there, or you can clone that repository and use all the same things we just talked about to add your files, add text for your tutorial, add config files and pictures for your tutorials. It's the same process. Everything's the same. So it's a GitHub repo like anything else. And you should have access if you're a developer. You have access to all the repositories.
Unless it's optional, I mean, as long as it's optional, then we will really rely on people's goodwill to improve this.
Yeah, and this is something we've talked about quite a bit. So we've thought about in the pull request process requiring it.
Is that possible?
It would be possible. I mean, we could just block. I mean, we could just not accept it until that happens. Now, I'm coming back to the encouraging people to contribute struggle between that and having everything perfect and everything ready. So far, I hesitate to require it because I'm all for growing things and making it as easy as possible. I actually feel your pain very strongly because I really would like to see more documentation and tutorials because I know we have a ton of awesome features that don't show up anywhere here. So this is something that personally pains me, but I worry that making it a box in the pull request is going to be so much overhead that it would slow things down.
Minimum, I mean, yeah, minimum documentation. Because, yeah, some of the features,
yeah,
you're totally lost. You don't know where to start.
Exactly.
It takes ages to get started.
Yeah, I feel your pain. This is maybe the open source thing. This is where it's a little tough because we're very much volunteer work in some cases. And yeah, there's this fine line between encouraging and people putting in the effort and getting developers. It's tough.
But I think the incentive structure is that if you're going through the effort of volunteering your time to put something in the open source, nobody's going to use it.
Yeah.
Unless you document it properly. So we need to keep reminding people that this is the case. Right?
It really does
Also,
amplify.
when you use it, you know how it works, and then you don't care if anyone else will come in.
Well, but I think if
that's what happens at the end.
Yeah, I think this happens a lot. But for let's say especially researchers or academics who really want to get visibility and get their papers shown and their work known, I mean, this is how you do it. If you put a tutorial up that has all of your stuff working, config files, meshes, a nice description, you link your paper, you have beautiful pictures. I mean, it's a win-win.
Or it should be more advertised.
Yeah.
Or
Perfect.
maybe it's not an option, but at least the minimum.
Yeah, I'm open to these ideas. My only hesitation is, people being discouraged because it's so much more effort just to write the documentation, and then they don't submit the pull request. So it's a fine line, but I would love a world where it's required. I thought about putting it in our pull request template, but so far I haven't done it. Yeah, question.
From user point of view, actually, do you have any list of which content you have in SU2? If we're choosing SU2, actually, if we don't know which content you have, then
yeah, this is pretty much the same question.
So basically saying in the front page, have a list, an exhaustive list of what the code can do.
Yeah, so probably if I'm from top machinery side, and if you don't have mixing plate kind of thing, then we cannot use this code.
Yeah.
And
So we used to have a
I don't
list
know, you
a long
have
time
that.
ago, but the problem is things change so much, and
Yeah,
It's worthwhile, though, maybe not in the front page, but a link on the front page, list of capabilities. Just to keep track, because there are people working on it.
yeah.
So you don't know where it is, you
Yeah.
don't know how to use it, right?
Yeah. So I mean, this would be a good hackathon topic for a little bit, right? So, finding a sustainable way to quickly do this. So yeah, question.
So the front page in tutorials is the right place for user documentation. Where should we put developer documentation? Not the kind of developer documentation that's just describing what your classes do or what the variables are, because that you can put in code and be compiled. But your actual implementation decisions that you take. I implemented this way rather than that way because.
Sure. Yeah, the only thing I can say right now is we have a small subset of developer docs here, but that's been pretty static, and it's not to that level of detail. I think a lot of that ends up just in the pull requests and the discussions. It's not really crystallized into a document or put somewhere, but it does live on in GitHub. So you can go look at pull requests, but yeah.
Even the folder of test cases.
Yeah.
Your development application.
Yeah. So I'm open to. I would love more documentation. So these ideas are good ones, and maybe we can talk more. Yeah.
About the documentation instead of requirements, and just some benefits for further. If you put in some biannual, semi-annual distribution of new documentation of new feature, which is attached to the web page, so everybody can reach it. They cover the last 3 most outstanding documentation of the new features. It gives some publication to the people, and people might strive to get into this position and without being required to do so.
Yeah.
Might be helpful.
I think that's a good point. The other.
We talked, right, last year, I think, about having some prices. This is what you're talking about. It's not necessarily
Well, we've tried a lot of things over the years to try to get more balance. This is a tough problem. One of the things, the reason I like this setup now with everything being on GitHub. So before it was a little more complicated with the documentation because it was on a separate, I think it was in Jira. We had, this has evolved a few times in the past 5-6 years. It was in Confluence, and then it was in GitHub Wiki, but that still wasn't available to all, and it wasn't in a repository format. So this is just within the past 6 months. We've put everything into a GitHub repository. So the idea is exactly, this is the best strategy I have at the moment to improve this, is that it's in a repository now, and everyone can write their own documentation, because it really is on the developers who know what they just did to document it, add documentation, add tutorials. So my hope is that in the same way we're sort of improving the code repo, we now have repositories in the same infrastructure to improve the documentation. That's my best strategy at the moment. That's what we've gone with. I'm open to other ideas. Mandating it, I'm a little hesitant on, like I said, but we need to do better. I mean, it's fair criticism. This is one of the biggest problems we have as an open source code. It's just documentation and where things are and what works, what doesn't work.
Or in this pull request, we can remind it.
Yeah, I am.
It can be a nice to have.
I think that's a good idea. I think we can do that today. I'll add that. Perfect.
Yeah, because I wouldn't have known how to do like add a tutorial unless you had specifically told me how to do it.
Okay.
And
Perfect.
Information about how to do it, and maybe even like the organization's a little bit limited. You can add like probably another, because there's like compressible flow and things like that. Maybe additional features for things that aren't necessarily
I see.
flow-based
Yeah.
Features would possibly be helpful so people can really get an
That's a good
idea of
idea.
what else SU2 can do.
It's a good idea. Yeah, the other thing is don't be shy. Create a pull request to the tutorials repository and just say, here's my stuff. Tell me where to put it. But I like those ideas. I think we should just in the template for the pull request say, we really expect or hope for documentation of this. Here's the link to the repo. Yeah, great idea.
And I think it's important. I'm just looking at the great adaptation tutorial. Yeah. I forget that it's a big GitHub repository. It's nothing.
Yeah, so these things it's really, really important to, but it's easy to get overlooked because we all like coding and hacking and doing the fun stuff, writing up features, writing code, and then once it works, we're like, okay, it's done. But nobody knows about it. So I keep coming back to this. If you really want to amplify it and have people using it and get your work out there, there's an incentive for you to do this. It's not just busy work.
So maybe what's possible is just create a template for each of the feature branches, so that while you're working on it, you can also already create a web page saying this is.
Yeah, you could create
put in
feature branches here.
Yeah.
So, I mean, in the same way, you can go and create a feature branch in the documentation repository and just be working it.
So question, I guess because of different repositories, I have to have a feature for my code development and feature for the documentation.
They're all separate.
We cannot have them, unfortunately, in the same feature branch.
No.
That would be nice.
Yeah, because they're separated, you just have to create the branch 1, 2, 3 times.
How about a minimum requirement when you issue a pull request? So just a one-liner that automatically enters the list of capabilities. So it's not obviously full documentation, but someone is actually aware that this feature is actually included in the code.
Yeah, I thought about things like this with commit messages, basically having some keys that we can do a search on.
Yeah.
Something like that. The problem with the pull request is I think that information gets lost once it's accepted. It doesn't go into the code repository, but it stays in the interface, like the GitHub. But I think in that direction could be interesting. Just we could have some keyword that we search for and then a option or feature that you've added.
Yeah.
Okay, that's a good idea too. Okay, we should keep moving and wrap this up. Yeah, we're going way over. Almost done. So then the other thing I wanted to say is I really recommend that everybody watch the repository. If you want to be up to date with what's going on, there are emails flying almost every day, multiple per day, people playing, working on pull requests, issues, comments, reviews, stuff's happening very regularly. And the only way to know everything that's going on is to watch the repository. So I can't encourage that enough. Even if you're not developing anything yet, you just want to know, get a feel for the pulse of what's happening, what the PRs are about, what's being worked on. That's critical because I've discovered that I think a lot of folks aren't actually watching. And then I talked to them later and I thought things were obvious that we had put pull requests in and we had done this and that and they had no clue. So this is another information mechanism. So please, you're gonna get a lot of email, but send it to a folder or something and just try to keep up. Because even just the one line like pull request for this, now you know something. Now you're up to date. Okay, this is more for later. You probably can't even read this. I put together a 9-step survival guide. So you can use this today. This is what you should do. Clone it, create a feature branch, activate the regressions in that branch, and then use that to guide your development. Work on your feature. And then if you're going to be working for long amounts of time, this was already said, you should merge the develop branch into your feature branch as you go. So every week, every couple weeks, something, merge the develop branch into your feature, fix any conflicts, and push it back up to the remote. So that'll get rid of a lot of conflicts, make it very easy to commit the PR later. Once you feel it's ready, submit a pull request. There's a template for you. Get reviews, engage with the community, fix the problems, address feedback. Any commits you make right there will show up in the pull request. I think this was already said. So you open a pull request, you can keep working and just fix things as the comments are made, changes, push them up. They'll show up as new commits and it will automatically kick off the test cases for you. So you just keep working on the open pull request. Okay, once it's approved, regressions passed, community will merge in your work, and then celebrate and proudly introduce yourself as an SU2 developer at your social engagements. So we did this last night after beers. I think we just walked around and told everybody.
I thought you meant Tell your friends and family.
Tell everybody. All social engagement. Christmas party, yeah.
See a little pins.
Exactly.
When SU2 developers.
Exactly. Okay, so it's pretty easy, huh? So just to wrap this up, we've put in safety nets and removed overhead wherever possible. So had you been working on the project maybe 5 or 6 years ago, it was a lot more complicated to do these things. These tools have advanced a lot. We're using all the standard processes. We're using the latest tools like Travis and pull requests and the whole ecosystem for GitHub. So the overhead is very minimal. You can make these branches. Branches are cheap. You can screw around. My encouragement for you is just to try crazy stuff. Don't be shy about breaking the code. Try to really do big things, and the test cases and the community are there to help catch you if you fall. There is no problem. I mean, this is how we keep making progress. We make big changes to the classes sometimes. We completely rip out classes and add new ones, and that's okay. We can make big changes. This infrastructure is here to support that. So with that, I think you can go ahead and start hacking. I think you're ready. Okay.
Thank you, Tom.
Yeah, so we prepared a couple of slides to illustrate essentially the reformatting of the input and output structure in SU2. Yeah, because for some of the projects we were working on, we were facing some problems with, especially when you look at multi-zone problems. Yeah, so problems with maybe multiple physics in different zones. Yeah, we have some proposals. It's not yet finished, but there is already a branch where some of the ideas are already implemented, but it's not 100% finished. And this is just a proposal, yeah, so which is open for discussion. Yeah, so this is, I think, the important point to make. So it's not set in stone. Yeah, so we are quite flexible on what we want to do.
Yeah. So the idea is that we wanted to make sure that any big structural change or any
Can you speak a little bit louder? Sorry.
So the idea is that we wanted to make sure that any structural change that affects everyone is discussed beforehand. So we don't know really what's the best way of doing that, but we thought that this hackathon could be a good idea. So there is already some branches in which both Tim and me have been hacking over the last few months, and we have put some ideas there for formatting the input to make it usable for multiple zones in a general or the most general possible way, and the same for the output to leverage on the class structures. So we prepared these slides. I don't know. And we are not going to go through all of it, but basically our idea was to identify some generality issues on the driver structure, which is the one that really deals with how the code solves the problems that we have at hand, and to link that to how we define the inputs or how we define the config. Because for some of you that are working with multiple zones, multiple physics, the input is starting to become the config file is starting to become a problem. It's starting to be too complicated or too specific. And for example, I came across these problems while trying to put a tutorial for fluid structure interaction, because there's no easy way to explain people how can you use this that links to how the code works for a single zone problem, right? And the same, we identify some issues on the output structure. So anytime that someone comes in and puts any new contribution and you want to output stuff to screen, we identify that that's a big barrier. So it's relatively easy to add a solver, it's relatively easy to add a numerical scheme, it's relatively easy to add a new boundary condition. But it is pretty hard to be able to output a new, like one magnitude that you might be interested on to screen or to the history file. So this is the kind of stuff that we wanted to discuss with you guys. So for example, about the driver, I just went to explain a little bit what we mean with the driver, what was the driver intended for. So at the end, a few years ago, there was only single zone. So you have one physical zone, and you could only solve problems for that. So I started implementing fluid structure interaction at the same time that other people were starting to be interested in different physics. And we came out with the idea of putting this driver, which will be responsible for interacting zones with each other and to transfer information between them. And then I went on to say what we mean by a zone. So basically you have that domain and you can split it into different parts, and each part can have different physical properties. So some problems that we identified is that originally the driver was thought to be opaque to the physics, right? The driver will only be concerned about this is what you have in this part of the problem, this is what you have on the other part, you communicate. But that is no longer the case. So you have specific drivers for each single problem. So if you have someone that wants to do turbo machinery using fluid structure interaction, right now you will have to do a C turbo machinery fluid structure interaction driver, which is not precisely a sustainable way of growing. Specifically, if that someone then finishes and goes away, and no one really knows how to hack on that part. We also thought that it should be constant in time, and ever since we put this together, it's been modified, this single file, by 486 commits, which is quite a lot, given that we have 5,000 commits altogether. And we thought that it should be flexible in structure, because right now there are a large number of hard-coded assumptions. So you want to do fluid structure interaction, your zone 0 is a fluid, your zone 1 is a solid. You want to do CHT, same thing. Your zone 0 is a fluid, zone 1 is a solid. You don't have the option to go to zone 2. You want to do multi-zone problems with different fluids, and you cannot specify different CFL numbers for different physical zones. Or you cannot say, oh, this part of the domain is going to behave with a compressible flow, but this other part I know is going to be incompressible, so I want to take advantage of that. You cannot do that. For example, for turbo machinery, same thing. You need a very fixed structure that for the person who has developed it is very obvious. But then when you want to, and again, I realize of these problems when trying to build tutorials, when you want to build a tutorial and explain people how to do this, then it becomes not obvious at all. And then what I was saying earlier, so combining features, it's pretty much requires a whole new development, while you are leveraging on a lot of solvers that are on specific classes that you could just potentially instantiate them and use them independent, right? So that's the kind of problems that we wanted to address. And I'm not going to go into all the details, but we have a branch there that is already working. So I exemplified it here with fluid structure interaction, because that was my first contribution to SU2, but that pretty much applies to everything. So I just to skip through this, well, you have a problem when you have different zones in which you have different requirements for the linear solvers or different boundary conditions. And it becomes evident that if you want to show anyone, okay, I want to do fluid structure interaction, and this is how my fluid config, so fluid only config looks like, this is how my structural only config looks like, but then I need to add these keywords there that are far from obvious if I want to combine them together. And that's only if I'm fixed to zone 0, zone 1, which someone may just want to have 3, 4 solid parts or different fluid parts. Same with this, you have an independent configuration file for your fluid problem, which has these requirements, but then you want to solve a structural problem in which you have a Newton-Raphson iteration with completely different requirements. And if you use these requirements for the structure solver, you will have completely unconverged solution. And the same can apply to any other new solver that people wants to add there. Again, you go to the multi-zone configuration file, things look very complicated because you need to add this FSI thing there. So I wasn't really able to explain that easily on a tutorial. I'm not going to go through all of it, but yeah, there are a lot of problems with, for example, you want to output the solution at different frequencies. You cannot do that. You want to output the surface from the fluid side, but not on the structure side because they are meaningless. you have two options: either you output both of them and you have a set of meaningless files, or you don't output and you miss some information. You also have to merge in all the files. So you have 5 zones and you want to do some sensitivity analysis on the meshes, and you have to add zone 1 coarse, zone 2 medium, zone 3 fine, start adding files to a very long mesh file. That's not precisely intuitive. And as I was saying, this applies to a lot of problems. So you have conjugate heat transfer, and you need to define CFL number for fluid and then CFL number for the solid. Solid incompressible temperature for the fluid and solid temperature, and you need to add this solid there. While the obvious thing will be there's temperature in this zone, and it doesn't matter what I'm doing. Or the same here, like specific heat, and you need to add specific heat solid, and that will mean only zone 1. And if you want to have same thing, multiple flows with different turbulence models or different compressibility regimes, Mach numbers, etc., you cannot do that. So our proposal was basically to go back to these 3 ideas. So the driver should be opaque to the physics. So basically just go from that list that we have to eventually go to a single zone driver, in which someone, which is a big percentage of people that only want to deal with one zone, they just go there. They don't have to mess with loops on zones or anything like that. So everything remains the same as it was. And then a multi-zone driver that is general. And that everyone that wants to work on multi-zone problems has to leverage on that. And then apply the same idea for the discrete adjoint. So for example, one of the stuff that I did in my thesis was to use the discrete adjoint on fluid structure interaction. We want to generalize that, so to be able to do discrete adjoint on multiple different problems at the same time. Again, we want it to be constant in time, so that's why I was saying any change that goes into a driver structure affects everyone. So we want something that is more or less constant. And then you have your problem requirements. You can just deal with that on the specific solver and the specific iteration. And that's also a problem with maintenance. So right now, that's one of the things that we identified, right? People comes and goes. There's some very nice feature, but no one can really use it because it's unclear. And to put together a tutorial, it's unclear how you explain things to other people. And yeah, finally, flexible in structure. So for example, going on with the discussion that we were having before, or of how should the code grow to be sustainable. For example, I agree with Tom that the code can still grow quite sustainable as long as we leverage on the class structures. So I don't think it's a big problem that we add lines of code as long as they are independent classes that at some point could be removed and no one else will be affected. But that's what we have to leverage on, also on the driver, also on the output, which I think we'll talk a little bit about. So I have a branch on this, and anyone that is interested, and for example, I was chatting with Antonio, and I think that this will affect a lot of people. And I have a branch with this that is already working for fluid structure interaction, for conjugate heat transfer, and for multi-zone fluids. And that has to be extended for harmonic balance and turbomachinery, and that has the potential to allow multiple zones, multi-physics on a much simpler way as they work right now. And without going into details, I've already managed to run like 3-zone fluid structure interaction that wasn't possible before, in which you can see, like, you can make the bottom beam a lot more flexible. You have a config file, and it becomes very obvious how you do it. Or for example, I played around with a test case that Tom put together on buoyancy, and I added a membrane on the middle. So I have 2 fluid zones that are independent, in which I could put different boundary conditions. I could put different physics. I put a membrane in the middle. The membrane is deformable. The membrane deforms, and the problem runs and solves pretty well. And for example, I also played around on this. I did it on an afternoon, and I'm not even sure that is working exactly, so I haven't really, but it becomes, at some point, it becomes very systematic how you set up a totally random multi-physics problem. So this is just, you have a flow that is cooling down this these pins, and you can just eventually just add the number of pins, different boundary conditions and everything, and the driver is able to accommodate this without having to develop a specific class. So I just listed some possibilities, right? So the first one actually is the one that I just showed, because that was added before I managed to get it running. But then you could have incompressible and compressible flows, you could have fluid structure interaction into machinery, you could have larger fluid domains, but only some parts could be deformed, and you could leverage on that. So you wouldn't have to have a very big mesh and deform it all, because that's a pretty large problem, or fluid cases with different requirements, etc. So that's one of the major restructurings that we were proposing, and then the output is another stuff that our team can describe.
Discussion on this first topic before we move to the second.
Yeah, sure, of course.
Questions, suggestions?
Would this mean that each zone essentially has a separate config file?
Yeah, so the idea is that there will be, so for single zone, everything will be as it is right now. And I think that's because right now a lot of people are using SU2, and you're not going to break everyone's things. But there's not so many people who are using the multi-zone or the multi-physics capabilities of SU2. So I think it's the good moment before people start using it. It's a good moment to actually define a way that is reasonable for everyone. So the idea, and this is again open to suggestions, I exemplified it here with FSI, right? So the idea is that you have this zone, this config file, which will be the master one. So you just run the solver SU2 CFD config multi-zone, and then internally there's this config list. So internally the code is smart enough to know, okay, this is multi-zone, so I'm going to read for zone 1, I'm going to read from this file, from zone 2 from this file, from zone 3 for this file. And you can actually just use the same one for 3 zones if you have 6. And all you will have to define in here is what's the interface between them. So you say, okay, this is my upper flow boundary, and this is my upper structural boundary. And these two are interfacing with each other. And that's pretty much it. Then time aspects, okay, because if you're running a time domain simulation, right now we're assuming that we have the same time step for all. If you're restarting the solver, and if you want to do how many iterations you want to do. And apart from that, then all the single zone configs will look pretty much as they will look for your single zone. So my idea came because I was trying to put a tutorial on FSI and say, okay, first I'm going to do a structural so people can know how to do it. And there's a set of config options. And then if you want to span that to fluid structure, then you need to explain people, okay, this option now becomes this other option. And I didn't think that was very good. So the idea is.
Can I ask a question, Ruben? So this means that I need to run, if I want to run a single zone simulation, standard fluid, I don't know, flow around an airfoil, I need to do SU2, let's say CFD, and then your multi-zone config, and then
no.
Okay.
No, that means that for single zone standard, everything is the same.
Okay.
And for multi-zone, then you run the multi-zone one. That is the one that defines what the zones interact with each other.
Okay. Fine.
So of course, if you are going to run a multi-zone, you will need to have the basic knowledge on what's your problem, your overall problem going to do. But the single zone will not change.
Okay.
Yeah.
So I like this idea a lot. I'm a little concerned that because of the nature of multi-physics, multi-zone, this requirement you had of constancy in time or stability of the driver script, that's going to be very hard, right? Because
I know.
Take fluid structure, which is your specialty. You want to take a fluid solution and a structural solution, update them, but you may exchange information in many different ways. You may have different time steps. Part of your research may actually be to march forward the structure and feed to the fluid, and march back and then march again, and Gauss integration points. So there are all these details that are going to be hard to generalize, right?
I know. So for example, I have some ideas here of. So for example, this is how a time loop would look. So overall, multi-physics. So you just loop on time. So you have this is the driver config. So that's the only thing that changes. and then you have to do a pre-process that is global to your problem. And then I added a switch here because you can run as an outsider, so updated solutions, or you can run as a Jacobi. So you transfer all the information that you have at a certain point, and you run each zone independently. And then inside of each of these, each independent zone does the same thing. So it does a pre-process and an update.
Is the pre-process now general thing, or is the PC?
So you have a pre-process that is for the general problem, and you have a pre-process for each of your zones, which is what you. So for each of your or for each of your physical zones, you will have your own pre-process, right? So you no, that's an iteration.
I think maybe we should. This discussion's really good.
It's
for
getting
tables,
very into the detail of it. So maybe this was just an idea to show to everybody the different topics of the hackathon, and this will be actually what,
yeah, that's good. You should chat.
what we will be doing in this afternoon. Okay, so
and yeah, we can just set up a roundtable and discuss all these details. So that's why I wanted to present some of the general ideas. So there's already a working branch, and we can just hack into the working branch, see how the details go, and then get input, because of course I am not so aware of how other multi-zone problems will work, right? So that's the whole idea of the collaboration.
Anyway, it was good to have a general discussion like this, because I think this is going to affect a lot.
Yeah.
This is a really important thing. But you know what it does highlight is that the SU2_CFD initially renamed as SU2.
We almost did a few years ago. We thought about making it PDE, but then we thought CFD is much sexier, and people like saying CFD.
I think it should be called SU2.
So
I think that the binary, you call it SU2, and then it will.
We can change whatever.
okay, so
Keep going.
second proposal, who wants to?
We still have.
Sorry.
Just 5 minutes.
Sorry.
It won't be that long because I will just state the problem what we have at the moment. You already saw that when Tom presented the class structure, that C output is one of the structures where we don't use any polymorphic behavior. Yeah? So we don't have any class structure there. So there's just one C output structure, and that's it. So all the solvers and all the drivers, they use always the same C output structure. Yeah? And if you look actually into the for example, convergence history body routine, which prints out the convergence history on screen and in file, you will see that it's just a mess, because we have like 1,000 if-else statements in there, and it's very complicated to add new output there. And then the other problem is that there is no standardized output to monitor the convergence. So everybody just hacks something in, and it looks then a little bit strange. The output. But the most important problem is that the output is not customizable. At the moment, because of course SU2 originated from external aerodynamics, and the output is hard coded, for example, in fluid cases to the drag and the lift. So that's also something we want to change. And then of course related to the things that Ruben was talking about, there is no proper multi-zone output at the moment. And we also don't have a solution at the moment for that, how the best way of doing that. So that's also open for discussions, because there is not the perfect way of monitoring convergence in every zone. And so these are just the problems that we identified. But the same as Ruben was talking, we also have some proposal for that. So our proposal is essentially, or what we want to have, is that you can really customize, for example, here the screen output in the config file. Okay, you can just say, okay, I want to have the external iteration number, I want to monitor the residual of the density and the residual of the momentum, and maybe also the drag. And then that this should work then. Of course, we may limit the output columns to a certain number, because otherwise it will be just too much. But of course, the user can also decide to monitor. I mean,
the default maybe be something nice.
Yeah, exactly. Of course, there will be some default fields like it is now. Yeah. So if this option is not there, then okay, the default output is just used. And one important thing is that the screen output is just a subset of information that we want to have in the history file. Yeah? So the goal is that everything which can be printed in the history file should also be printed. It should be possible to print it on screen. So they should use the same structure. Yeah. So, and this is just a proposal. So the history output should look essentially the same, but we want to group certain things so that you don't have to say, okay, I want to have drag, lift, side force, and all the aerodynamic coefficients. So they should be grouped. Yeah. So you just say aerodynamic coefficient, and this is printed to the history file. And the same then for the volume output. Yeah. Oh yeah.
You might want to add the option to control it by runtime for that. So while the code is running, you may change your idea about the structure of output. You want to change that.
Yes.
Right now, actually, runtime does that only change the number of iterations.
The runtime.dat is
it's a hidden feature that you
it's a hidden feature. Yes, we thought about also extending that to other config option. Yeah, that would be one application. Yeah. Yeah.
Application is probably out because you thought about something and you get the code is running for so many hours and
exactly.
You thought that this is not what you expected and you can change it on the fly. And,
yeah, that would be also a good feature for using it. Yeah.
But that requires some signals on the process.
Not necessarily because it keeps running runtime with that every time and time.
You're saying rereading the file. So we're always checking to send a signal for a file every iteration.
Yeah. That requires some work because it depends on where you do this pre-processing to check what output you have and things like that. But I think it is possible. Yeah.
Have you thought also of not just having labels for what it can be printed out to the screen, but also having some user-defined ones where you have a simple callback? There may be something.
So in this
where the user defines the label and defines the information.
Yeah, but of course you have to do it in the code. In the code, right? But there's actually right now it's a very easy way of okay, you cannot see, you can see. So what I did at the moment is that there's you have a class structure now. So there's C flow output, there's a C incompressible flow output, and all you have to do essentially to define a new output is to change something in this particular CPP file. Yeah, so you just have here add history output. You define the name, so this is what you would describe in the config file. Then the label, the header in the history file, what is printed there, the format that is used for screen output, and then the group here. Yeah, this is all you have to do. You have to add this line, and then also later to add this line here so that it knows where to find this value action. Yeah, so you have to add 2 lines, and you have to recompile only the CPP file. Yeah, so to add a new output. So this is probably what we meant.
Are they separated so that you can decide to put in the history and in the monitor? So if I don't want to see something in the history, but I want to see the monitor.
Yeah, they are separate. Yeah, but everything you said here can be used on screen and in the history file. But you can specify different things for what you want to output. Yeah.
So one thing, actually, what I'm thinking about might also apply for the input. But I was thinking if we can actually have the code consider the input properties and output parameters dynamically. So if you have an XML file or something, as I said, I was initially thinking about the input. If you have an XML of the properties that could be read and any dependencies, for example, if you use this solver, you are expecting these parameters. So that would actually make it easier for someone to add a new property. I'm not sure if that makes sense.
You mean with property, you mean a config option?
Yes. So that and also an output parameter. So I think it's similar to what you're proposing there, but it actually happens dynamically rather than having to recompile the code.
For the config structure, I think it will be very complicated to do that on a dynamic way. That requires.
It's pretty nasty. That's one of the few places where we use templating and We haven't changed that much. It's easier to add an option. It's not easy to change that structure of how that all happens. But maybe bring that discussion in with.
Yeah, we'll have the discussion later. I'd be curious, is the concern the consistency between those different parameters or in the config file, or? Yeah,
so basically, what I'm talking about is, remember when I started out with that passive scalar, so tracer. So first of all, there was some inconsistencies about how the array of properties were in. So that's something, and everything suddenly collapsed. And also then it's a question of how do you actually add it in the config file, how do you actually add some keywords like the config file. So I was thinking if you can have something that describes what dynamically what properties go for each solver, then you can also have some clever way of indexing that specific property in an array, so you don't actually have these issues when you add something. Again, you're probably right, it's probably impossible to actually.
Well, I wouldn't say it's impossible, but it's
not a nice thing to do.
It's not a nice thing to do.
It's the classic word, non-trivial.
Non-trivial. It's really non-trivial.
Okay.
Yeah, and just one last word. I mean, the same thing then, of course, also holds for the volume output. Yeah, volume output is essentially the same. You just add 2 lines, and also later where to find this value, and you're done. That's.
Is this in a branch somewhere, Tim?
So we have a feature reformat config branch. There's a feature output branch, and there is a merged one. So feature input output.
But maybe hack on them separately, and then.
Yeah.
And then you can merge 2 groups. Okay. Like it.
Great. So you know that they are the guys that you like to talk to this afternoon about these aspects. If you're interested, then we had a couple of other proposals. So maybe who wants to be next? The only question that I ask you is please try to be a little bit concise and to the point, because
let's try to be hacking by 12. So
yeah,
yeah,
exactly. So we're done with this. Okay, so thank you, Ruben. Thank you, team. So who wants to be next?
If you want to say something, get up close to that laptop.
Okay. So the proposal.
Get behind the podium in front of the laptop.
So the proposal that Brian and I had was, it's not as general, it's a little more specific, is to be able to restart a RAN solution from Euler restart. It's useful for when you're doing big configuration aircrafts, being able to first do an Euler simulation, which is less expensive, and then be able to interpolate from that, from an Euler grid to a RANS grid, and then be able to start a RAN simulation from there.
And this is more generic, I imagine. You can start from a coarse RAN solution or fine RAN solution.
Yeah. Also that. So being able to interpolate between meshes that occupy the same area, essentially, is also one of the.
You guys know that already, that capability exists in separate pieces of code, right?
Yeah, I think that's what Brian said, that Vic is using it. So we should be able to reuse that. It's just a matter of putting things together and being able to like initialize the turbulent variables to the right things and things like that when you don't have the information in the Euler restart.
Because you experience, getting complete solutions to converge from free stream can be very difficult. So yes, I agree.
I think the important view is the interpolation from coarse mesh to final mesh. Much more important than which physical equation do you solve.
Mm-hmm.
To totally change the line of working that you are doing. The approach is very difficult. It's a very important feature.
Mm-hmm.
It has a no slip.
Yeah.
There are issues, of course, when you go from coarse to fine. At some points, the fine grid may fall outside of the coarse grid.
Sure. There are a lot of things around that can cause problems. And also the different type of meshes, how to interpolate it. Side graph or radar, the interpolation should be different.
Yeah. So that's what Brian and I were thinking of
working on. So if anyone wants to help and join in on that effort, we don't have a branch yet. This was literally thought of last night. So yeah.
Oh, but now you know how to make a branch. So yeah.
Thank you, Giant. What's to come next?
So we're mostly working on an incompressible solver. So like we had two things in mind to work on today. So I'm doing a pressure-based solver. So just wanted to clarify some, like the implementation boundary conditions and so on, just to, there were some differences which I needed to clarify. And the other thing was the actuator disk implementation. So we ported some of those things from the compressible to the incompressible, but the mesh doesn't seem to run. Like if we make a new mesh, it keeps giving us some weird errors. So we were looking to fix those errors. So we'll be here.
Well, great. Thank you so much. There was someone else. Sorry, I forgot. Please.
Okay, so the idea is kind of the same as Ruben present, but instead of talking about zone, can apply it on point. For example, if I would like to run a multi-point optimization, and I want to supply a different configuration file for each point and different meshes that share the same area. For example, with a lift, with a flap, and I want to examine liftoff and cruise, and the flip is in a different orientation, but the FFD is in the same area in the wing. So the idea is to supply a multiple configuration file, and then we can change the physics, all the parameters, the physics or the schema.
Okay, great. Great idea. Thanks a lot.
Generalizing it is, yes, tricky. It's an important one.
Any last minute? Yeah.
So inspired by this increased generality of the output and so on, the other day I wanted to implement a new objective function, and I found that to be quite a pain, because that turns out you have to go through lots of different files and putting things in different places, and including changing the base solver class to say that the solver can compute a new objective function. So I was thinking if there could be a more general way of defining objective functions that doesn't involve hard coding stuff into the base solver class.
I suspect there was an idea earlier to these output fields to implement there actually.
That was somewhat related to output. Yeah, there are some hooks to customize. There's a custom objective hook that you can just populate, but you're right, it does track all the way through. And all the plumbing is there for it to work, but if you want something altogether new, it's probably a bit of work. But yeah, it's related to some of the output stuff. We had thought about moving where you evaluate things like force calculations into the output structure. Yeah. Is that still part of that plan? Maybe you could team up. But...
Yeah, exactly. Yeah, also these specialized output classes, they also deal with computing something that you don't need in the solver.
Would that become the objective function location then? Would you move it from the solver to the output? Yeah, so maybe you could bring this idea in and work with the output.
For example, for turbo machinery, all the objective functions are already in the output physics and are moved away.
It would be nice to have these two things merged, because think of it as if there's a black box in the output, should be something that could drive an optimization either from the objective function or the constraint function. So if it's all localized in one spot, then we can also make sure that all the derivatives are computed correctly.
I mean, this is critical, people.
Because, for example, for differentiation, the adjoint solver classes will usually ask for the objective function and so on. So that part is not done in the output.
Yeah, exactly. We thought about also moving drag computations also to the output, because that's nothing the solver needs. It's just for output purposes.
Anything that doesn't impact the solution, you can move it.
Excellent.
Yeah,
Thank you so much.
That's a great.
Anyone else?
Are you guys going to chat about this?
Yeah, then probably we have one last one that we are proposing, and this is going along with some new developments that we will be presenting tomorrow, and it's called what we call SU2 NEMO, which stands for non-equilibrium models. And this is a joint effort between a lot of people, Strathclyde, Stanford, Bosch, people from VKI. So you will see tomorrow more precisely. But here we have one hackathon proposal, and the idea was to start looking at a way to addressing multiphysics, but in a different way than respect to what Ruben was saying, in the sense that we want to be able to address chemically reacting flows, including the possibility to address multiple equations for the energy, so multiple temperature equations that comes from, for example, high Mach flows, high Mach regimes, or that comes from, for example, the interest in simulating some combustion going on for house appliances and so on. So the idea is to start brainstorming about how shall we deal with all these different models that will have to come into place regarding thermodynamics, equations of state, chemistry, so constants of reaction and so on, in a smart and cohesive way, looking at, on one side, aspects purely on the configuration file, which is probably the most critical point where we really need to avoid messing things up, because it could become a showstopper. And from the point of view of the interface between libraries that could provide some information. Again, I was mentioning about constants of reaction, reaction rates, transport properties of mixture species, and so this will be the basis of the discussion. So really start thinking at practically how we want to go ahead with this. Niso, you wanted to add something to this?
I completely agree. It's a very important topic, and I think it's important not to immediately
set in stone
open up
things.
an editor and start coding, but
just
think really hard about
how
to set it up, because else 2 or 3 years from now you get into a problem.
Yeah, and I'd like to say that in that discussion, that everybody who participates, you should also look and see how other people have dealt with this. I mean, other communities probably have tried this already.
Yeah, we were discussing this earlier with Niso, with some examples. Daniel, any comment you want to add?
That's great. I think along those lines, just for everybody in your projects, even if you can't write the final solution down in code, a slide that says what you thought about and your strategy is great for output of today as well. So yeah, spend time thinking very hard about what you want to do. Even that is excellent output. Something tangible, and that's great.
Okay, great.
Mike, a very quick question. So is this project regarding actual thermodynamic models? So think about the physics, or is it how to incorporate it? So is it a software engineering project, or is it a physics project?
It's both.
Okay.
It's both, in the sense that there will be some really heavy surgery on the code itself to introduce both numerical and physical models to address this type of flows and applications. But given the fact that, as usual, we don't want to reinvent the wheel, and for sure there are people who are experts in certain areas, talking specifically about people at VKI who have this very nice library of thermochemical properties and so on. We want to combine this sort of software engineering elements in order to find the best way to interface with the external libraries and.
But the hackathon project is more about the plumbing to make sure you can do this and enable research in the physical models that then will be easy to plug into the existing infrastructure. At the moment, it's complicated, right? If you come up with a new physical model and you want to plug it into a reactant flow capability, it would take you several years.
Great, thanks.
Yeah. Okay, great. Any other question? So then just to wrap up, we have a few hackathons, couple of hackathons coming related to input and output structure, and people are Ruben and Tim. This other topic that is to Giant and Brian related to restarting a solution from a previously Euler solution and then going to runs that involves aspect of mapping of meshes and so on. We have topics, sorry, I forgot which one was. Incompressible flows, right? With that, then we have these aspects related to cost functions and optimization strategy that maybe could be linked somehow to what Tim and Ruben are proposing. And then we have the other proposal related to, again, the possibility to address surface movement control and then do multi-point optimizations and addressing different meshes, different configurations, different operating conditions. And then eventually there's the NEMO.
And there's also the driver structure part.
Okay.
Just the input output.
Yeah, correct. Yeah, for that.
Okay, good.
Good. So we're writing them down. So probably we'll put up a slide that summarizes what are they, and we'll put it there such that we know what's going to be discussed.
And so a couple slides at the end, we could just make a blank format or something in the next few minutes if people want. But we'd really like to collect this and post it at the end. I mean, maybe I'll take some pictures of the room, show us working. We want to capture this, right? Let's not lose what we do today. So yeah, add some of your slides, even add extra thoughts or things you worked on, and we'll capture it.
And this could be a branch, but it could be a future branch, right, of the code that others will work on.
Of course, if you can create a feature branch and work directly in the code today, do it. If you get stuck and just need to think about strategy, then make a slide on strategy. That's fine too.
So after you present these slides on this work, is there any discussion about that? Also, get inputs from the other groups, because that could be useful.
Exactly. We left 45 minutes, but we're running a little behind. But hopefully, well, we can wait for beers. I think maybe an extra half hour, right? If you guys are okay with that. So I'm hearing some dissent. I don't know. We'll see. But that's the idea. Yeah, some good discussion because we're already starting to get into good discussion about the details. But let's let the groups work in parallel, flesh it out, and then come back and discuss.
The idea is 2 slides, right? For a team, and then at least 5 minutes discussion or more for.
Yeah, so there is not a direct connection between number of slides and number of slices of pizza. So you get yeah. Okay, great. So I don't know if you want, Tom. Okay, maybe we can just start, and then when pizza comes in, we just really, as one said, very informal, very easy. Okay.
Okay. Yeah. So we have just put together the driver stuff with the input and output because at the end they both link together. So we have been chatting over there about, well, first the realization that we really need to improve this input output, especially for multi-zone problems. So we had a nice chat with Julio about stuff that we will need for moving meshes, and with Antonio as well. So there's a lot of interest, and we really should get into this soon enough. So we agree that generalizing the driver structure is a step forward. However, there are an indefinite number of multi-zone problems, right? So we should attempt to go for something that is as general as possible, but we will need help from the community to actually extend that. And then, yeah, there are some problems already covered by the proposed methods that we showed you guys this morning. So we were thinking that we could just put a pull request so everyone can get to see the code and see where this is going, and then we can just discuss the stuff on there. And also, we just wanted to know that there's a lot of non-glamorous work involving on doing all this restructuring. So yeah, this will require a lot of time investment by all of us. So just as a note that we will appreciate every piece of help that we can get on this. Then, with respect to the output.
Yeah, with respect to the output, we just agreed also that we have to leverage more on the polymorphism for not only for the output structure but also for some other structures we have in mind. So, for example, we figured out that it might be necessary, for example, to have objective functions also as some kind of class structure, right? And there we should also leverage on this polymorphism, of course. Yeah. But there we have to discuss further whether we want to have it in the output, whether it's a new class, right? So where we want to put that objective functions. Yeah. So that's the these are still things we have to discuss. And then something else we also figured out is that when we go on with this input and output reformatting, then there's still the Python structure that needs to be adapted somehow. And yeah, I don't know if there are people who are familiar with the concept or the structure itself that we have. It's relatively complicated, I would say. Unfortunately, the people who developed that are not there anymore, I think. Or the people who started that, right?
Friends mostly.
Yeah, exactly. So it's quite complicated to get to know the structure of this thing. So if you want to change it to have new design variables or new objective functions or whatever, so which are not designed, not for aerodynamic design, yeah, then this is complicated. But I think we have to do that also.
So also for multi-zone, the Python structure is very rigid and it doesn't work for anything that it goes beyond a single zone. So that also is something that we should accommodate.
Yeah, so the Python structure really needs some major rework, actually. Yeah. This is something we all agree to. Yeah, so
I think that's pretty much it.
That's pretty much it, and there are still a lot of things we have to do. But we will open these the things we have as a pull request, also the output thing, and then people can already see whether they can fit their things or they can already modify their things according to that new structure. And if there are some questions, we're happy to help. Yeah, that's it, I think. Thanks.
Great, thank you so much. Any question? One.
Not a question, but on the last issue, I agree. And, you know, Tom will remember years ago we thought, and the OpenNDAO people at NASA wanted this, to have an OpenNDAO component that was essentially SU2. We may want to reconsider that now that OpenNDAO is in much better shape.
Yeah.
It's Python driven, it's much more flexible to define optimization problems and various other things. And SU2 can be the engine that provides function values and derivatives.
Yeah, maybe that would be much easier than developing.
Yeah. It's actually already in the work plan for the project that we have with but it's a bit further down the line. So.
I think we should talk about it as a community because it would take the burden off of SU2 to do all that optimization, right? Setup. On the other hand, it is kind of nice to download SU2 and be able to do optimizations without installing anything else. So there's a balance, but it's an approach to not have to deal with all this stuff ourselves.
Yeah, yeah.
But then focus more on this output structure, so you generate functions and sensitivities, and then let the optimization, non-linear optimization, probably be defined outside of SU2.
That might be one approach. Yeah.
Then that also solves the idea of how we want to input and output the data, because then we already have a structure that we will need to match with. Right? So, yeah.
Great, thanks a lot. Thank you, Ruben. Thank you, team. So, who is the second?
So we initially wanted to sort of do the heterogeneous restart, which means sort of being able to restart RANs from Euler, but some other people came in and saying, oh, this would be super useful. So we sort of wanted to generalize it instead of talking about restarting solutions to just general mesh interpolation from course define, find the course, whatever you might want to do. So the problem we stated in a more generalized fashion would be interpolation from a source grid to a target cloud of points, essentially. This could be then whether it's a FEM mesh or an SU2 mesh or anything of that sort. It would trying to make it as general as possible. Most of what we did today was sort of think about how we would go about it. The easiest part is interpolating for points within that lie within the source grid itself. For those, Edwin has written numerous sort of routines to find the containing element for any particular point that you might want to search within a mesh. And you find the containing element, and then you would interpolate between the points of the element and the coordinate that you're looking for. What becomes a little more tricky is when you have points outside the source grid. Even though the mesh should encompass the same area, there might be points outside the source grid, because if you have a more refined mesh, it'll do a better job of staying true to curves, which might result in points outside the source mesh. What that would cause, then in that case, we would have to sort of extrapolate from the surface element, the closest surface element, as opposed to a containing element. And this may result in some non-physical points like negative velocities, which would actually make a restart solution worse. So there might be some requirement for a little bit of post-processing to correct those values. And so this is the discontinuities is a point that was brought up by Iran. He said that there might be an issue when you have shocks, whether in the interpolation of those points within the shock from a coarse grid to a fine grid. Not entirely sure whether it is going to be an issue, but if it is, we might have to do some pre-processing, find shocks, and then have some special treatment for the interpolation in those regions. So one issue that we sort of are kind of sidestepping is the issue of parallelization. So if we had to do a restart, like actually have run SU2 CFD from a restart that is of a different mesh, we'd actually have to rebalance all the nodes after the mesh has been interpolated, because then you have, before you have a coarse mesh and a fine mesh in your memory, and you're interpolating. But once you're done with the interpolation, you need to get rid of the coarse mesh and then just work with the fine mesh. And so that would require some rebalancing. We can sidestep this by saying that this, by making this interpolation sort of a pre-processing step. So have use SU2 solve to sort of interpolate the restart onto this fine mesh and then start your solution. And that would, I guess, make things a little easier. Now, we have to go about and do all of these things. And if you guys have any suggestions, any issues, we'd love to hear them. But that's about it. Yeah.
Any comment? I want, so regarding this aspect of points outside the source grid, how are the guys from INRIA dealing when they do mesh adaptation? So they always need to have a CAD definition on the background?
They either have like a higher order representation of the surface, or just a really fine surface tessellation that they can then interpolate on.
Yeah.
So this is the same type of approach that you might want to consider, or?
We would want to consider that at some point, but we were thinking in the near future we would just use whatever interpolation routines are already present.
It may be necessary to map that coarse grid cell when a point is outside to the true geometry, so then it's guaranteed.
Yeah.
I think the other thing that I just thought about that I didn't mention earlier, and I have a question about the discontinuities. In the RAND situation, once a good wall function formulation is in place, you'll have some coarse grids that can provide a good initial solution, but a knowledge of the fact that there's a wall function formulation there might be good too.
Mm.
You see what I'm saying? So you would interpolate the solution, but not just do a linear interpolation
Between
the
the
first thing element, but rather have an idea of what the wall function is there. So if additional fine grid points fall within the cell, you'd actually capture the boundary layer profile. So that may be a neat thing to add that doesn't take very much out.
Yeah.
On the discontinuity, if you start from a coarse grid, you're going to have a smear shock in some senses. When you go to a finer grid, you're going to have not a true shock, but a compression area. But that
it might be okay. Just that it should be checked.
Yeah.
I guess if the problem is just normal, totally normal, okay. If it's a huge shock, you might lose the form of it or something.
But if you use it from coarse to fine, you won't be using.
Well, fully. I know.
Actually, you know what you're saying is. Sorry, I just thought if you have a shock in the coarse grid that's aligned with the lines, and then you put a fine grid that is perpendicular to it, I can see that you can get in trouble with it.
Yeah, I think what's important also that this is done, should be done in stages, starting from simple project and going more complex, using more complex situation. So it will be running and people will be using it. And the best tester of any code are the users. Because they fall into any bit that the developer has it.
Yeah. Yep.
Great. Thanks a lot.
I have one more.
Yeah.
So you're gonna keep it inside of SU2 SOL, right? So
I think so. Yeah.
what are all the use cases? Is there any reason to move it to CFD, for instance, eventually, or I don't know. I've thought about that much.
Yeah. So that would, the use case would be if you want to just restart from like a restart that's existing in an Euler simulation and then going into a RAN simulation. If you just want to be able to do, oh, okay, I'm just going to do a config file that restarts from this mesh, then we would need to be able to do the rebalancing and have to do it in CFD.
So I had one thought about this when I was talking to Shravya about it when she was working on this branch. The other thing we always wanted to do that many people have asked for are probes in the CFD solution for unsteady. Probes, yes, in the CFD solution for unsteady. And a lot of the stuff you would be setting up here, it'd be nice to have them, at least the classes, in common also.
Okay.
So that CFD can pull those routines in, and any of the modules can pull them in because.
Well, actually, a lot of it would be in, because most of ADT structure, structure is in. So all the searching routines might be like the interpolation schemes we can also put in the common structure, and then almost everything except for the little information passing is done in SU2.
As some of you know, Eduardo Molina arrived at Stanford maybe a month and a half ago or so. We've had this discussion with Evelyn as well on how to set up both the acquisition of unsteady data from unsteady simulations, whether it's URANs, ES, or even the high order solver LDIs, right? And the post-processing, keeping time averages, looking at two-point correlation. So there's already some initial work in this direction.
I think the averages are already there. That's something we did.
But we need to extract a lot of like Reynolds stress distributions and various other things for which Eduardo has a bunch of post-processing scripts. We just want to make this a standard thing for both solvers. And then this idea of probes, whether they're point probes or line probes or plane cuts or things like this, we really want to standardize that as well. Yeah. The same search.
So it's just a comment to think this has a lot of other uses, so let's keep it in a very general place so we can use it for as many things as possible.
Yeah.
I was going to, my friend around here, and I probably the oldest one. So there is an application that you were asking about that we used to call grid sequencing. So full multigrid or full approximation storage multigrid, FAS, starts in a coarse grid, which may have multigrid itself, right? And then after it done some steps, it takes that solution as an initial condition for a finer grid, which may have multigrid again, and these could be nested. So it may be that just the Greek sequencing approach like that one is a very robust way of getting complex random solutions.
Yeah.
Also, the common practice in the LES, you're doing very fine meshes in the end. You start with very close mesh, get a solution that is meaningless, just playing and then to refine. So it's a common process how to get into properly resolved solution.
And even for the course LES, we use RAND solution, right? More for DES is what we do as well. We just do steady state RANDs or just use that. So yeah, a generic way of doing this would be very important.
Okay, great. Thank you so much.
So, so this is the project that Nimrod proposed earlier. So it's basically on multi-point optimization. So very briefly, the concept is that if you are to optimize a design, you should consider all the relevant physical conditions that design would actually be in. So as an example here, if you want to optimize an airfoil, so if you want to reduce the drag of an airfoil, you actually want to consider that airfoil during takeoff and during cruise. So for example, during takeoff, you would have a different mesh first of all, and you would also have, for example, lower Mach number, etc. While in cruise, you might have a higher Mach number. So another example is sometimes you want to have different numerical parameters for the different cases that you are considering in order to speed up convergence, or even in some cases, you actually don't have different numerical parameters to actually achieve convergence, so to avoid your solution to diverge. Anything you want to add so far? So what we would like to eventually do is to have multi-point optimization where you can actually use a completely different configuration file for each of our optimization points, so for each of the cases that we consider. And as I showed with the case of the airfoil, we would like to be able to use a different mesh as well. Now, also another thing that from what I understand, is not currently in the capabilities of SU2 is that we would like these optimization points to run in parallel. So theoretically, they're completely independent. So there's no reason why we should run them one after the other. It should be quite easy. They're inherently parallelizable, so it should be very easy to run them in parallel. So the easiest way we thought about going around doing this is, rather than actually messing up SU2 itself, is to actually have a Python wrapper that can basically start with a certain number of processes to run these optimization points, or actually each optimization point would correspond to a cluster of processes, because then each point could run in parallel. Then once those finish, the Python wrapper collects the results, optimizes, rerun, etc. So this is something that Nimrod quickly drafted out. So yeah, as I said, basically the initial process will be a Python wrapper. It will create n amounts, n number of processes, or as I said, the cluster of processes. So so in this case, if it's the first iteration, you calculate the adjoint solutions, you optimize, you go up. If your new design decreased your objective, so again, in the case of the airfoil, if you manage to decrease the drag, you go again and re-optimize. Otherwise, you do line search to adjust the coefficients, etc. So again, I don't know if there's anything you would like to add.
Yeah, I think the idea is well understood. The needs of multi-point optimization with a different configuration file is the right way to achieve the goal of optimize realistic problem.
I guess the point is that there are two levels of parallelism, right? There's parallelism at the level of multiple points of a solution.
Yeah.
But then you have multiple adjoints for each of those solutions if you're seeking derivatives for more than one function, right? So not only the multiple points can run in parallel, but the adjoints can run in parallel.
right? Because they are independent. Each case is independent in the other.
I should mention that all the issues were discussed with Francisco, and everyone was quite interested. I mean, he started the present relatively not so developed multiple sheets. He sounded quite interested in pushing that forward.
It'd be good to check what the status is.
I think it's still pretty basic. I think it's just a handful of options for aircraft multi-point. It's not, it's pretty specific and kind of hard to.
Any further comments, question?
It's somewhat linked to what I guess Tim and Ruben were talking about, right? It's really more flexibility in the way in which optimization problems are set up and executed.
Yeah, it's a very similar problem. Yeah, the only difference, I think, we're more flexible in having a Python wrapper for this. It's probably easier to implement.
I guess I don't know for a fact, and maybe Beckett knows this, but if OpenMDAO were the driver for optimization, does OpenMDAO have a capability of executing very different function-graded evaluations in parallel and launching things in clusters? I opened this thing one time, so it may be that much of this can actually be farmed outside, and so you don't have to write all the Python stuff. I don't know if the runtime execution environment is sophisticated enough to do that.
It's an important cluster to connect with OpenMDAO or to write that file.
Yeah, well, because there's an effort already, like I was saying, connecting SU2 with MDAO, OpenMDAO. Right.
But we can do this in SU2.
Yes, of course.
Great, thank you so much for this. Okay, so maybe you want to take the stage and discuss about it. Okay, very good.
So in this NEMO project, there are quite some different groups involved, and many of them want to use different combustion models in the end. So first we talked a little bit about how applicable the framework in the end should be. So should we have one big framework for all the different combustion models, or should we separate the solvers? What would make more sense? And then in the end, we came to a conclusion that it's possible to have one common framework for different combustion models and different fluid descriptions. And then we thought about what's best or how the input file, the config file should be written for the different things. And I think this gives an example now which keywords we would like to introduce to the config file. So I think the example here is closest to the finite rate model that we are going to implement. So we use a keyword for the mechanism file and then specify, maybe I go first here, specify the models that are used to describe the whole mixture, so a mixture of different gases or different fluids. And then those are basically mixing laws, which will then be used to compute a mixture generalized viscosity or conductivity based on the different species viscosities. And those are specified with those keywords here. So now the next step will be to get in touch with all the other groups and sync with them and talk back to them what their ideas are on that, and then take it from there. So I don't know if you guys want to add something or.
You want to say something about Kempkin,
Oh yeah,
speeches, and various
yeah, good point. So we also talked a bit about different chemical reaction mechanism file formats. So there are a bunch of different formats out there, and we think that it makes much sense to use one which is very popular and commonly used. For example, a Kempkin format, although Kempkin itself is a non-open source software, but it's used in many other groups and many
mechanisms are published in this format. So our proposal would be to use that format for SU2 as well.
If you can maybe add a couple of comments. So this was our attempt in trying to rationalize a little bit a way to introduce the various requirements that we need to address multi-species flows. We also discussed about the solver itself. So we also discussed about the fact that we are probably going towards a solution where we will be introducing a new solver that will, let's say, come and add the list to Navier-Stokes, Euler, and so on, to take care of these type of applications. And the idea will be that all these equations that you will see together tomorrow, but so mainly equations of conservation of mass, momentum, and multiple energies will be solved in a coupled fashion other than in a segregated fashion. So these were some of the ideas that, again, as Daniel said, we are going to propose to all the people involved in NEMO, and then broadcast. Probably could be a good idea also to put down a pull request such that we can really raise more feedback on these few ideas that we have laid down. Any comment?
Would you say something about what kind of external software to SU2 might be needed in order to compute some of the species material properties?
Yeah, at this time we are focusing on a couple of external libraries. One is called the Fluid Prop, and is a library that has been developed by people at TU Delft, so Matteo and his collaborators, Piero and so on. And this is a library that has a lot of capabilities in terms of addressing the thermodynamics of complex and non-ideal gases. The other library is a Mutation++, developed at VKI, so von Karman Institute for Fluid Dynamics. And this is a library that has a lot of very detailed database for thermochemical properties. So not only transport properties, but also reaction rates for a huge number of species, including ions and electrons. And we've also been discussing briefly about Cantera, which seems to be a sort of let's say a mirror of Mutation++, which is very widely used in the industrial context, but maybe it has been used a lot for low speed incompressible flows, and we haven't come to a final decision on which one to use. Probably we'll go with Mutation, mainly because we have in the group the guys who are the developers of Mutation, which gives us a good reason to have Mutation other than the other. And we will discuss a little bit better on this tomorrow on the NEMO presentation. Mike?
One thing, I've actually seen a few papers that in order to resolve the viscosity or to actually improve the equations of state, they might use molecular simulations or coarse-grained simulations for a short period of time, extract certain properties, and use those for the CFD simulation.
You mean concurrently with the CFD? Or?
Concurrently, or maybe serially, or just for a very small time, trying to do that, then feed the CFD solver with enough information to get maybe as boundary conditions or kind of tweak the equations of state, and then you get going. So it sounds like something that's going to be way in the future, but
that's a very interesting thing, actually.
I can probably find a few papers and send you.
Sure. It would be greatly appreciated. Sounds very interesting, actually. Any other comment? If not, then thank you, Daniel. Thank you, everybody, for the hard job. So I guess that we can conclude this first day, which was a nice day with a very nice weather outside, but we stayed inside. So thank you so much.